Okay, hello everyone. How are we doing? We're all good? We had a great time yesterday? All right, well we've got a lot more to go through today, so again, I'm so excited to have you all here again. I am just going to go through a few things that I missed yesterday. It will be mainly just the safety stuff for anybody who wasn't here yesterday but is here today, and then we're going to get right into the action. So, welcome to Rust Nation Day 2. You're all at the brewery. For those of you who weren't here yesterday, the fire exits are all noted. There are accessibility, there's a lift, and any accessibility needs can be met by our volunteers. And again, if you need any help, you can find one of our volunteers who are stated on their badge, and you can also find some of the Vitis team as well. Again, if anything else, you can also come and find me. One of the things I kind of messed up on yesterday was the whole magic show, right? So everybody thought it was going to be this big Las Vegas-style David Copperfield show, but it was literally a magician walking around with like card tricks. So I should have clarified that. I didn't. So I apologize if you're all expecting some big explosions and razzmatazz, but that didn't happen. We just had a guy with card tricks. Are we gonna have a social today as well? Yes, we are gonna have a social today. And will we have the magician walking around with cards? No? Okay, so we're just gonna have drinks and lots of fun and networking. So I think that's a lot, that's a lot better, right? Okay, so here's the Wi-Fi password as well. Again, if any of you haven't joined the Slack yet, please do. That will allow you to network. That will allow you to connect with each other after the conference and continue all of the good vibes. Also, the live stream, we had a few issues with it yesterday. We've resolved it now. And please share this with as many people as you can. Please tweet it out to make it as accessible to people as possible. Again, very thankful to our sponsors. We want to shout out one in particular, well, two in particular, because they're having competitions. Realm, our recruitment partner, are having a competition, and many of you have already played the game in the exhibitor room where you have to tap the lights and everything else. Have you? Have any of you tried that? Good, good, good. So you have a chance to win a pair of really nice headphones. So when you get a chance and when we're doing a breakout session, please go over to the Realm team. They are a lovely team. They are our official recruitment partner, and they'll, have some fun at their booth, do their competition, and you'll be in a chance to win some prizes. Also, Fastly are doing a raffle as well. So if you go into the Fastly lounge, into their demo lounge, pick up a raffle ticket. You'll also be able to win some prizes from them at the end of the day as well. Now, I am really excited to introduce our next speaker. He is our opening keynote. He is someone that we all know. He's the reason why we've all battled with the borrowed checker, right? So please give a big hand and welcome Nico Matsakis.
Let me unlock my computer. Hello, everybody. Welcome. I would like to see my slides. There we go. Okay. Yes. Hi. So I'm Nico Matsakis. I want to point out all these slides are online, minus the last commit that I didn't push yet because I didn't have the Wi-Fi password, but now I do. So we're all set. But if you want to follow links and things, you could do it that way later. So who am I? I've been involved in Rust a long time. I've accumulated a number of different roles along the way. So, first and foremost, I work on the language design. I co-lead the language design team along with Tyler Mandry, who's here somewhere. Woo, Tyler! Together with the other members of the language team, like Josh Triplett, also here. We decide what goes into Rust, what does not, more importantly, I suppose, and what the heck this language means and that kind of thing. I am also a senior principal engineer at Amazon, and that is a pretty cool job because I get to go talk to the teams at Amazon that are using Rust and figure out, what's working for them, what's not working for them, and then kind of bring that back to the Rust community, mingle it with everything that we hear from everywhere else, other companies, other users like you all, and try to make it better for everybody, right? So it's pretty great. By the way, if any of you are using S3, EC2, Lambda, blah, 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 you're also using Rust, which is really cool too. Turns out there's a lot of people using Rust at Amazon. I'm also an intermittent, bursty blogger. By intermittent, I mean I'll occasionally write like 3 posts in one day when I get excited and then go 3 months, as you can see here, because I've been too busy. But I try to keep up, and it's a great place I highly recommend blogging if you just want to have a log of what the heck you've been thinking over the last N years. So, what am I wearing today? None of these hats. I'm here just as myself, telling you what I think. I certainly am not representing the opinion of the language design team. I am also definitely not representing the opinion of my employer, which I would never presume to do, but I'm also wearing all of them, right? Because I'm kind of informed by all those different roles, and that just affects how I think. So, Rust in this time, like ever since we started, I would say, has always had this consistent North Star that we're working towards. We want to empower everyone, and I think that word does a lot of work. We really want to broaden the pool of people building reliable, efficient, and particularly maintainable software. And I think Lars did the great job last night hitting on this theme. We're designing for the long term, right? We want Rust to be used to build software that's going to keep running after we're gone, after your children are dead and that's a little morbid, but down the line, right? We want the software to keep running and keep working long after you've forgotten it exists. So how do we do it? What is our most important value? Is it reliability? Is it performance? Productivity? I think it's none of these things. They're all super important, but the one that I most value and cherish is actually this other one, stability without stagnation, that we talked about in Rust 2015 in 2015 when we announced 1.0. It's basically saying, look, we know we're not going to get it right. Nobody can get it right the first time. We're going to try really hard. We're going to get it as close as we can. And then we're going to learn from what we did and iterate and iterate and iterate and make it better and better and better and keep working towards that North Star, even if we don't ever get there. And I think that spirit is so important and a big part of what we've been able to do and what we need to keep doing if we want to keep growing and improving Rust. So, in that note, I should note that the addition is one of the cool tools that I'm happiest with. We are, every 3 years, we try to make a new addition where we allow to make just a few tweaks and changes to the way the language works. But the nice thing is, it's opt-in, and so your old code keeps working. Everything interoperates, and you don't really have to care about it if you don't want to, but it will make your life better, right? So I'm pretty happy with that as a mechanism. We're planning to do it again this year. I don't think we have any major changes planned, but that's kind of the idea. It should be small stuff, add a new keyword, that kind of thing. So, I've gotten a little bit obsessed lately with trying to write down what is it that makes Rust, like, rusty. And that's because I found that if you can articulate this stuff and say it, you can actually stick to it much better than if it's kind of a rule that you intuitively know, but you don't really know. So this is my latest version. I haven't even updated the various websites that I have. You're seeing it here first, but I'm pretty happy so far with like 5 properties that I think kind of go together to make Rust into what it is. And I'll go through them real briefly, but we're going to see them throughout. The start, reliability, you know it, you love it. If it compiles, it works. That's basically it, right? That's what we're shooting for. If it doesn't work, it's not, it's your fault, right? Not Rust's fault. And that's cool. That's going to happen too. Performant, well, what we're really shooting for here is, yes, the first draft of your code should run pretty well, but not that you'll never have to optimize. You will. But you don't have to optimize by going down to low-level stuff. Like the high-level stuff should still compile to fast code. You may have to change what it does, introduce caching, do other things, but you operate at that level of abstraction. Let's see, low level. Right, if you want to count your allocations, we want to help you. If you want to count every bit and account for it, we want to help you with that too. I've noticed sometimes that's necessary. We're targeting system software. It can be really low level. I've noticed that sometimes, though, people take that to an extreme. Shout out to Andre, who's been giving this talk, I think for a while now, but who certainly gave right there, on easy mode Rust. You will make your life better if you don't count all your allocations, trust me. I think if you look at experienced Rust developers' code, you'll see they use the fewest, they choose when to use the right features. That's kind of the art. In any case, that's there. Extensibility, look, some languages try to give you everything packaged together, ready to use. That's not Rust. We try to give you a pretty good starting point and the tools that you can build your own or take advantage of what other people have built, which I think is more scalable. And finally, accessibility. Now, I'll be honest, I wish that I could write here easy to use, but I think that's not, we all know that's not always true. And that's partly because building software that's going to live and run for a long time is actually just hard, right? We can't actually make that easy no matter what we do. But we can make it easier, and we can support you as best we can and find opportunities. And so that's really what we strive for, to be accessible to get started and supportive as you go along. Okay, I want to walk through an example. Iterators, you've probably all used them if you've used Rust, but I think they embody a lot of these properties. And to do it, we're going to tell a story with Barbara. This is Barbara. She's a Rust programmer. She's building an app. She's also a drawing my daughter made several years ago that I've just fallen in love with and I have to keep using forever, much to her chagrin. And one day she comes and she needs to make a bunch of thumbnails from a list of images. So she sits down and she writes some code like this. You've probably written code like this before. It's a good example of this composability, where you can take these little constructs like map and just put them together to build a more complex program. What's cool is this code will compile down to something much simpler, right? It's going to look something more like this when the compiler's through with it, as long as you remember to use -- release, which you should do, especially if you're benchmarking. And so, in fact, this low-level code that you didn't have to write, it's actually got a few things in it that maybe you wouldn't even have thought to write, right? Like pre-allocating to the right capacity or skipping the bounds check. We could use Unsafe code to show that, because we know that it's in bounds already. This isn't like a real iterator. So this is sort of the promise, right? That you can get pretty good code, but you can do it without having to drop down to this low level of abstraction. Let's see. So what about extensibility? Where does that come in? Well, iterators are just a library. They don't use anything that you yourself can't use when you build things on crates.io, right? And we can show that because, hey, maybe Barbara's coming along and she says, my app could go faster if I could run this thumbnail generation in parallel. There's really not any reason not to. And she could go use Rayon. Now, full disclosure, I wrote the first version of Rayon, but really Josh Stone does all the work these days, so love you, Josh. Not here, sadly. There are a lot of good Joshes in the Rust community. I don't know if you've ever noticed this, but Josh Stone. So she drops in, she gets Rayon off of crates.io, and she just changes iter to par iter, and she's off to the races. Stuff's running in parallel. That's really cool. That's another part of Rust promise. But that's possible because we didn't try to build everything in, right? We made it possible to add these things after the fact, and people can come up with ideas that we didn't have to start. So what about reliability? Where does that come in? Well, to do this, I'm going to introduce Barbara's intern, Alan. I love his arm, just like coming way around there. So Alan is, Barbara's been running this app for a while, but she has no idea how many thumbnails it creates. So she says, Alan, I'd like you to add some telemetry. Alan's like, cool, I'm going to do it. So Alan sits down. He says, okay, I need to have a counter. It's going to start at 0. I'm going to add 1 every time. And then I'm going to log it. And great, this looks good. And Barbara comes in and she reviews the code. She's kind of hungry. She's thinking about something, next level and wizardly. And she's like, you know what? Yeah, this looks good. Ship it. It goes out. And what happens? Well, it turns out there's like a subtle bug in this code. You can't actually add 1 to a counter this simple if you're running in parallel, because you're going to get the wrong count. It's going to be a data race. And so what happens is the code ships, they get telemetry, but the values are all wrong. They don't actually know how many thumbnails they're making, and they reallocate resources and all the, oh wait, no. No, that's not what happens. I'm sorry, I forgot. We're using Rust. Let's rewind. what happens? Okay. Alan's writing the code. He says, okay, I'm going to log it. Let me just compile it. And then the compiler says, whoa, buddy, no, sorry. You've got a data race, man. You can't do that. And Alan's like, oh, cool. Thanks, I learned something. No, okay. Sorry, that's actually not what happens either. That's what I wish happened. What really happens is the compiler says, cannot assign to counter. It is a captured variable in an FN closure. And Alan says, what? Rust is really hard. How does anyone do anything in this crazy language? Barbara! And then Barbara says, oh, yeah, I've seen this before. Okay, it's a data race. You got to use atomic usize. That's going to make it safe. And then Alan's like, oh, cool, okay. Now I know I'm feeling next level. Now I can go be a better programmer. When I'm writing other languages too, I'll avoid this mistake. And if you grew up in the 80s like I did, you cannot say, now I know, without showing G.I. Joe and saying, and knowing is half the battle, right? That's kind of the promise. That's what we're really shooting for. And I think Felix Klock, sadly not here, but a longtime colleague, put it best with this hack without fear. You can build stuff. You can even build fancy stuff, doing parallel stuff. And it's going to kind of work and be maintainable, and you're not going to lose control of the code once your intern comes and pokes at it. So this is really cool. I have a quote. I don't have as many awesome things as Lars did. I'm really jealous. But I do have this quote from someone inside Amazon talking about this experience and how it applied to S3. Right? And so here they took a library that was written in C. They rewrote it in Rust. Why that's interesting? You can tell the language didn't help them make it faster, right? You can't get faster than C. C is the best. But it did actually, though, help them get faster because they were able to feel more confident. They understood what was happening. They knew the compiler would help them, and they could do fancy optimizations, and they got big wins, right? So this is sort of the promise. Okay, enough about iterators. You get it. You've used iterators before. Let's talk about the future. And by this, I mean the future of Rust. I also mean standard future. This pun never gets old. I want you all to know you should use it. And async Rust, right? How many people here have used async Rust? A lot? Okay, cool. So you know then that async Rust is the set of language extensions and libraries and things that let you build really efficient network services. I can say that wearing my Amazon hat, it's kind of a big deal, over there at least. But in general, everywhere else that I've gone to, it's become a really hot area for Rust. It's one of several kind of killer apps, you can call them, killer domains maybe, also embedded, some other things. And so it's something that's pretty interesting to me, right? And I think our design is actually really cool. I can't take credit for that. It's a bunch of other people's work. But it builds on and embodies a lot of these principles that I've been talking about. And let me explain how. So imagine, here's how it works in JavaScript, okay? Which looks syntactically similar, but it's actually different on a deep level, right? In JavaScript, I might have a function, an async function, and when I call that function, like here, if I'm starting from one task, I'm effectively starting another task, right? And it's very cheap, they've made this very optimized, but still I have two tasks running concurrently, at the same time. And then I can await my promise, and when I do that, I'm effectively blocking and gonna wait until the other task finishes, and then I'll get its result. Okay, that makes sense, that works, it's a nice setup. It's different in Rust, right? Because in Rust, when I call this async function, I start in one task that's currently running, I call the async function, but I don't start another task. Instead, I get a data structure, like an iterator, a sort of lazy future representing an inert, suspended computation. Nothing is happening, it's just potential waiting to be realized, And then I can await it. And when I await it, I don't start another task. I take my current task and I say, let's breathe life into that suspended computation and move it along and execute it until it's finished. Right? So I'm making use always of this task that I already have to run. And why is that cool? Why is that? It kind of seems just different, like it's a lazy, and in fact, that's what I thought for a long time. But no, it's actually very cool. Why? Because it lets you build up these computations into more complex ones without adding cost along the way, without creating lots and lots of tasks as you do it. Right, so imagine here, I'm going to process row 1. I have one function. Now I'm going to process row 2. I just have 2 data structures, both very cheap. Now I'm going to make this joined future. That's going to put them together and run them concurrently, but it doesn't do that right away. I'm still just building up the program I'm going to run, so I'm just putting them together and copying some memory around, very cheap. And now when I await, I'm actually going to run the 2 concurrently from within my current task. Right? And so we're able to build up more complex control flow without adding cost that's like proportional to how complex it is. You know? And that's really cool. Because, yeah, okay, we can join 2 futures, great. Well, but as you add more and more levels, those costs, well, they don't add up because they're not there, right? But they would if they were. So, for example, we could write code like this. This code can run a query against the database, get a list of rows, then start working through the rows one by one, mapping and doing parallel or async processing on each of the items that it's fetching. And then it can do it buffered. So you're doing up to 5 at a time, but no more, because that would use too much memory and be kind of expensive, and you don't want to have your peak memory usage go up. That's really complicated when you think about it, what's happening here, right? But it's like 4 lines of code. Cool. And then I can pull them out one by one, and I can process them and upload them or do whatever, right? So that's pretty neat. That feels a lot like Rayon. That feels a lot like iterators. This is kind of what we're going for. So what's the problem? Well, actually, no, not the problem yet. Foreshadowing. We're going to get to it. But right now, we're still in the good stuff. And because I'm not allocating tasks and doing all this other stuff, hey, I can run it on, I don't even need an operating system. I could use Embassy and run this on my sensor node and do cool stuff like that. That's pretty neat. OK, now we can get to the problem. The problem is, in my opinion, async Rust today is awesome, but does not yet fulfill all of our goals. In particular, it's falling short when it comes to reliability. And let me come back to this really cool example. If you actually ran this code, and I took this from a bug report, you will find that your connections sometimes time out. Why? It's very subtle. Well, it's because, remember, when we make one of these computations, nothing is happening, not right away. So we have a task, we've made this rows computation that's going over the database, and then when we actually await an item, that's when we breathe life into it. Yeah? So it starts executing. Right here, the 5 connections get started, we're pulling things from the database, we're doing stuff, and then one is done. And when it's done, it goes back to being suspended, and it's not happening, nothing's happening. And then we go do the uploading, and we're busy with that. We put all our attention into uploading. And in the meantime, maybe the database is trying to talk to us and send us more data, but we're not answering because that computation is suspended. So nothing happens. So it times out. It says, OK, fine, I'm going to stop talking to you. And now we get errors. And that sucks, right? That's like what the other that's what the other languages do, not Rust. It's supposed to work. So it turns out there's a number of patterns like this that come up. We've gone through and done a lot of talking and discussion, and we've kind of identified them. I think this is the 5. There's probably some more. If you'd like to learn more, we did this cool thing with the Vision doc. I really loved it, where we wrote up a bunch of stories, but there's also a bunch of great blog posts. You can follow those links. The good news is, I think we can fix it. I think we can make it better. Yeah? We've been making some progress. So I think this is kind of my look back on historically what has happened with async Rust. We started with async functions. We spent a few years building out amazing stuff in the ecosystem. Shout out to Alice Ryle. She's somewhere here working on Tokyo, but also the shuttle folks and a bunch of other people. And we've been working now back on the language side, sort of building out async functions and traits, and listening and learning from that experience, right? And we've got more good features coming. But these tools, I think the next step, right, where I think we should go, where I hope we get to, is using these tools to build up better APIs. APIs that let you gracefully handle cancellation, streams, avoid those kind of foot guns, and interoperate more easily, so that I can have one library that works just as well on Embassy as it does on Tokyo and so forth, right? Which today is harder than it should be. So I'm really excited about this work. I'd love to talk to you about it. I think there's a lot of work to do, but I think we see a path and we're going to get there. So where else can we do better on reliability? Well, how many of you have heard of CVERS? Okay, not that many. That's good. Don't go look it up. So, this is a pretty funny project actually, which caused me a bit of headache from time to time, but that's okay. Which exploits a bug in the compiler that's been there a really long time. Which it's all my fault. It really definitely is my fault. Which exploits a bug in the compiler or a bug in the language, depending how you want to look at it, to let you write safe code that will crash your computer and do all the things that Rust is not supposed to do. So how many of you are worried about this? Okay, some of you. I'm worried too. I think we should fix this. It's not the thing that worries me the most, though. I'm more worried about this, which is a little more not so glamorous, but which is to say I'm worried about, we lean hard on extensibility. We've got all these crates that do cool stuff, but that means that if you're using a bunch of code, you need to be sure that it came from where you thought it did, it does what you think it did, and it's not like a Trojan horse. For a long time, this was kind of a problem because our infrastructure team was like well, first it was Alex, then it was Pietro and Mark. Pietro's here somewhere. It wasn't enough. We didn't have enough resources here, and it was hard. But things have gotten a lot better. We've got the Rust Foundation. We've got a number of people paying attention to this. There was a great talk from JD. There's another talk coming up. Walter Pierce is going to talk about Painter. Super cool. So I think we're actually we're making progress, and we're kind of raising the bar and doing innovative stuff. And I'm super excited about that. I think that's really important. And so that's one of the ways that I think we're doing better on delivering on our core promise and where we have still lots of work to be done, right? But we also do want to fix CVERS. And part of the reason we haven't done it yet, that it's been such a long-standing bug, is because it took a lot of refactoring needed to get done in the compiler. I guess it's two things. One, we didn't think it was actually going to affect people in real life, which I think is true, unless you go use that package, so don't do that. But two, we also knew that it needed a bunch of refactoring and improvement and to get the kind of reasoning that we wanted the compiler to do. And I'm happy to say we're starting to make great progress. Shout out to Bastian, who's here in the audience as well, in the new trait solver and some of these new refactorings. And so I think we're going to be in a better position down the road to really kind of close out these soundness bugs for good, finally. And also make a bunch of other cool improvements. Things like async functions and traits and so on are building on these new capabilities that we're adding into the compiler. Oops, okay. Now what about the spec? So there's another area. Traditionally, Rust has not had a specification because it didn't seem like the most important thing to do. I think that was right. But times have changed. We've got more resources. We've got a lot more success. We're starting to shift our attention. And also, hey, Ferricine went and did a bunch of work, shout out to them, for authoring up a spec for their own purposes, which they generously open sourced, and we can use as a starting point. So now, thanks to Mara and other people, Mara's here, we're starting to make progress on that and get to an official Rust specification. There's no timeline, but we're making good progress. And that's really cool, right? That's going to let us better understand what Rust does. I also think it's really going to accelerate our ability to develop Rust features, because it's helpful. That's what I'm most excited about. But it will also let us, together with some other work, to build out theorem provers and solvers, which I'm really excited about. I'd like us to be able to take unsafe code, the really widely used unsafe code, like the standard library, and mathematically prove that it is in fact not unsafe, right? That it can't have undefined behavior. And to do that, we have to extend the compiler, some work that's ongoing, to offer up some of its information so that we can build tools like theorem provers, like Connie and these other ones, to make use of that and prove things about your code. So with all this, where are we going? Where do I want us to get to? I want to get to the point where when you have a widely used, super important package, like say Tokyo, that makes use of a lot of unsafe code, I'd like to be able to say, hey, that unsafe code is fully verified and proven. Now, in CI, Okay, it's a long road from here to there, very long. We'll be starting on core and standard, I imagine, before we get to Tokyo. Maybe we'll never get there, but this is my dream, right? Is that this is kind of the standard we hold our widely used packages to. I don't think it'll ever be practical for everything you write, but for the stuff that's widely used, it's worth the effort. Okay, cool. What about accessibility? Okay, how many people here like Rust error messages? Yeah, this is what it looks like to me. I'm glad that you raised your hands because I would have looked really dumb with this GIF otherwise, but I was confident. So we've put a lot of effort into our error messages, and they're an important part of how people, I think they're an important part of Rust success. Like I usually say, I've literally never had, and this is true, a conversation in which someone with a new Rust user who didn't talk about error messages. Like they always come up. But remember, there's still room to do better, right? All too often, we're telling you things that are about sort of how the type system works instead of about what your bug is. And that translation is kind of the learning curve. That's that famous, like 2 months, is learning how to go from what this is to what it's supposed to mean. And it can get worse. This is from Diesel, where they model the schema with, or database schema with traits, and you know, I don't know, I have no idea what this says, but it basically says you should have had an integer, but you have a character, or something like that, right? So we're making progress. We have built tools in the compiler that we use to give better error messages, and we're starting to export those tools out to the ecosystem. Diagnostic on unimplemented is coming out soon, maybe May 2nd, very soon, which will let you customize what message you get if a trait is not implemented. And then there's work like the translations work that can make it more accessible if English isn't your first language. So I'm really excited about this direction. And I want us to step on it. You know, we can go so much further than this. We can do amazing things. Yes, we can do your diagnostics. We could give you custom lints. What if your crates came with lints like Clippy, but customized to the crate to say, hey, don't use my API like this? That's a mistake. Okay, what if they were like integrated into the IDE, giving hints and refactorings? I mean, this would be so cool. I think we have a taste of this today, right? We use procedural macros. They're very simple. They just like take text tokens in and spit text out. But still, we can build up Serday and derives and custom derives and all this really cool stuff, shuttle and all this stuff on that, right? How does all that work? Well, it's all based on this one simple thing. What if we could give more information to those? What if they could integrate more deeply, like access the type information, read the rest of the program, not just the stuff in the macro? I see people who work on the compiler being like, Nico, oh my God. Sorry, that's what's happening. Get on board. No, all the other stuff the compiler knows, right? I mean, and I kind of already hinted at this when I said verifiers need to access the information the compiler knows. I think we're on our way. We see a path. It's a long road, I know, but we're going to get there, and it's going to be awesome. So this is where I want us to go. I want to give the tools to build rich developer experience. I don't want that to be just a part of the compiler. I don't think that's the Rust spirit. I want those to be everybody's tools. So macros, derives, whatever it is, you should be able to do it just as well as we can. All right. So what's really cool about Rust values is that they support each other and they build on each other. And if we're doing all of them, we get this like super-powered, empowering thing. Any one of them is good. All of them together is even better, right? So we have things like, we've seen that extensibility can also be helpful to accessibility. Custom error messages and so on is one example. We've seen that reliability helps accessibility because there's nothing less accessible than debugging a data race. Like that is the bottom. So everything above that, good. But what about accessibility? What does that do? In my mind, that supports everything else. That's the fundamental layer. And why? Well, because Rust is open source. You know, it's this like magic thing. You got, oh, hey, you have a cool thing, people are using it, they come up with ideas, some of them actually go and implement those ideas, and then the thing gets better, and then, oh, it's still getting better, we're in this big cycle, and everything is great right up until you burn out, at which point it seems less good. So this is all true, but this is also true. And we need to work on this part, right? And I think this is a problem. It's not a Rust problem, in my opinion, although it does happen in Rust. It's just a challenge of making sustainable like software development. But there's some peculiar characteristics that come from open source. And I think part of it is coming from, hey, you have a lot of users, and from them, some percentage go on to be contributors, but an even smaller percentage of them go on to be maintainers, people who take care of the software over the long term. Like, it's really great to write a PR. It's even better to review the PR, right? And even more exhausting, actually. So what is maintaining, anyway? It's a lot of things that you may not realize. It's reviewing, yes. It's also all these other things, and I'm sure I've left off a whole bunch. And there's a huge set of people whose involvement, like in the Rust open source project, comes from doing these kind of activities, which seem invisible and don't often get the shout-outs and credit that they deserve, but which are absolutely essential. Absolutely essential. And I think if you have ever thought, I would like to help the Rust project, I would like to be involved in the community, I suggest you don't go find an issue to implement. Don't do that. Instead, come and talk to the triage team, or talk to someone else and see if you can get involved at one of these levels, because that will really help you. That will really have an impact that is super hard, super huge, and get you a lot of, we're all going to love you forever. Okay, this is important. I think also we can make this easier, better, more well-loved. We can make a lot of improvements, and I think we have a lot of new tools at our disposal. We've gone from the compiler being largely volunteer effort to a lot of folks being employed and paid to work on it full time. That's really awesome. We have the Rust Foundation, starting to do more and more collaboration, a lot of great stuff going on there, and I think we're just thinking about it a lot and trying to do more stuff. So where do I hope we get to? I'd like to see a rich and diverse set of people working on the compiler, both as career maintainers who do it professionally and volunteers, because there's room for both and they're both important. And a community where everyone feels welcome, and most importantly, where we have clear pathways how to get involved and how to stay involved and broaden that involvement and sort of progress along your journey, right? Because a lot of times we pay attention to the in-funnel, but not so much the other parts, right? So I want to end this talk. I'm a couple minutes over. Some of you know that I started out with 60 minutes last night, so I'm feeling pretty good about coming in at 32. I wasn't really reading how much time I had. It's all good. I want to give a shout out to the Rust Nation team, especially Ernest, who I know, the rest of you I don't know, but I'm sure you did amazing, important things, for bringing all of us together to have this time, letting me talk to you, letting me meet all of you. You may have noticed I tried to make an effort to call out some of the great Rust people who are here today. There's a lot of folks from the Rust maintainers and community here, and that's all thanks to the work of Ernest. So, thanks very much for that. And hey.
Thank you for embarrassing me. We can't have questions because we're running a little bit behind, but please give Nico another massive hand. Okay, so we're going to have a room change now, and we're going to have breakouts into the other tracks. Again, please remember the Helsing Hackathon is also happening today, so if you want to get hands-on with some things as well, please go to the Helsing Hackathon as well. So enjoy the rest of the day. Hello, everyone. How are we doing? I keep asking that because I want to see how the energy levels are, you know? It's been a great 2 days. Hoping that you're all enjoying the talks. We now have a very special speaker, someone that we all know and love. Please welcome Tim McNamara.
Thank you so much, Ernest. My name is Tim McNamara. This is Unpacking Unsafe, just in case you went to the wrong room. Otherwise, we might call this the title slide. So I'm just waiting for it to come on screen. What we're going to be talking about today is memory safety. And in particular, this idea that I'm not a Rust expert, and there's this kind of dark, dangerous corner, unsafe, that I've been warned about. Like that's for like real Rust programmers. And what I want to do is demonstrate how people actually end up using this in the Rust community, and how you as a maintainer of a library or an application can review code that might even contain unsafe, and whether or not this is something that you might need to consider. So, my name is Tim McNamara. I'm from a small, strange country, often left off the map, called New Zealand. I run a technology consultancy called Accelerant. My lead brand is this thing called Tim Clicks. And I'm on the planet to build a better planet. I genuinely believe that Rust can step software forward. And some of the most critical problems that we face today as a society that is digitally connected and has software inside the fabric of everything we do requires a continual focus on reliability and security. You are very welcome to go and find me online. This is my book. One of the interesting things about Rust in Action is that it will actually enable you to build real applications. And we do actually talk about a few things like, how do we use this? Well, what does unsafe even mean? And so that's the plug for the book. The agenda today is pretty straightforward. Here's not many people like watching a 90-minute presentation, or a 55-minute whatever. So here's kind of the 90-second version. We use Rust, even though it might be difficult, it might be hard to learn, because it's supposed to be memory safe. But there's kind of this ability for us to sort of unlock the keys somehow. What does this mean? We've got this unsafe keyword, and it turns out that about 96% of all downloads from crates.io will have unsafe in their dependency tree. So saying we don't have unsafe in our code doesn't mean that your dependency or your dependency's dependency excludes unsafe. So it's still part of your job to understand enough to be able to go and check. And this is sort of we're going to wrap up towards the end. So I just want to start. I have 3 little girls, and we spend a lot of time watching Bluey. And one of the episodes is called The Fairy Tale. Bandit here. Bandit is the dad. He's talking to his 2 daughters, Bluey and I've forgotten her name. Bingo. About a fairy tale land called the 80s. And in the 80s, they didn't need safety vests. They didn't need hard hats. We're not in the 80s of software anymore. We actually need better tools. And this quote didn't work very well. If you have a very large code base, let's say 1 million lines or more, at least two-thirds of your security vulnerabilities are going to be due to memory safety concerns. This has been independently corroborated by multiple places. And Rust is a very, very good way out of this. except for the fact that Unsafe exists. Now, there's a problem, because culturally, the Rust community is allergic to Unsafe. So here is a report from 2020 where the lead maintainer of the Actix web framework, which at the time was the highest performing web framework in the world, and was essentially put up in a pedestal as one of the lead Rust projects, says, I'm done, I'm out. And the reason why this happened was because the Actix web framework was created on sort of an internal system called Actix. And Actix was an actor-based system which enabled sort of pre-async Rust. Enabled people to kind of create a little worker that cooperated with the other workers that are all operating at the same time to perform requests and responses. Nikolai Kim was a staff member at Microsoft, but he did this on his own time and received a huge amount of vitriol because of the use of unsafe constructs. Now, it turns out, and so the response was like, I've checked it, I'm good enough. Like I went in, I'm sure that this is okay. It's like, no, it's not okay it's not okay for the peak Rust system to heavily rely on Unsafe. This is actually not very good for the Rust community. And so kind of you have this tension between the maintainer and between the ecosystem. And it turns out that the ecosystem was right. There were soundness flaws in the implementation. So let's talk about what Unsafe actually unlocks. Less than you might think. So here is, some ordinary Rust code, and what I want to do is kind of dig into it and say, here's a pointer to the first element. And I take A, or let's say a reference to A, and I want to cast this as a mutable pointer to an I32. And that's fine. And I'll just go down to, so this is a memory address. We can figure this out by taking pointer 1 and asking for a memory address. And I can, then we get an error. Casting an, that I can't do. I thought this was fine. Okay, well, I'll just do this as pointer. Yeah, we'll try this. Aha! So Rust compiler is actually going to be a little bit smarter already. We can't just kind of wildly cast references around. That's kind of nice. And I'll just run this code. We receive a memory address as output. That's great. And so we don't need Unsafe to access a pointer. To create a pointer. And it's like, for whatever reason, I need 2 vectors. I want one that has 1, 2, 3, and one for whatever reason is 2 and 3. So let's go and increment my pointer. I'll need to do something fun, which is cast it as a U size. So it's just live coding is actually quite hard when you're on stage. It's quite prone to sort of typos and things. It's kind of intimidating, really. And I just want, actually we'll define this as mutable and then increment by 4. We need to increment by 4 because that's the width of an integer of I32. And now we can build up a vector from raw parts. And pointer 1, where does this point to? It points to the number 2 in the heap. The length field we can just define as 2. In fact, I'm going to sneak, I'm going to say it's A length minus 1, because I want type safety. Duh. Capacity. Minus 1. So I'm totally safe here. And we can even, we get a compiler error. This operation is unsafe and requires an unsafe functional block. Okay, I'll do that. So I'll create, I've gone and created a second cursor, which is also helpful. B is unsafe. And I can actually print out B. Well, let's find out. Will this work? Matching closing delimiter. Actually, I can fix that. That's a typo. Ah, superb. This is why this is called mob coding. It's a very it's like unmatched types. I found a use case. Okay, so I'll cast this as a mutable pointer back to an I32. I don't have access. There we are. Love you all. And goodness gracious. Okay, so just in case anyone doesn't know Rust. Oh, it doesn't have a different display. Okay, fine. Okay, Rust. Thank you, I appreciate it. Cargo, oh no, we'll hit run here. 2, 3, perfect. Is it a free invalid pointer? What? Maybe I'll just turn off all the rules. I'll just use release mode. And I'll just use so here we go. It's package bin A. Copy. Close this down. Run release bin A. Core dumped. So what have I done? Why is this wrong? We are dropping the vector twice. This is implicit in our code. What we've introduced is a memory safety vulnerability, unsoundness called a double free. Rust at the end of an object's lifetime will delete the value or invoke the drop trait. It does this for A and says at A, when A gets to the end, when it is no longer available, on 13, it is dropped. But I also then drop B. The reason why it does it twice is because I have told Rust that I will comply with its rules. Unsafe enables you to tell Rust that you have complied with its ownership and lifetime rules with pointers. That's all that you get. You still need to make sure, you still have a type system. So we can't do something like put a float in here. The length is 2.0. You still have a compiler. It's still going to make sure that you are doing the right thing. The unsafe keyword only unlocks a tiny slither of extra behavior. It pushes the burden from the compiler to you. It pushes the burden from the internal machinery or the logic analysis system inside the compiler to your brain. And because there are many things because your Rust program exists inside the context of other software, we might have to interact with the operating system. The operating system can really only give back a pointer and a length in the same way that I've kind of magically created a pointer and a length. By the way, we don't need to do for. I could use size of, and I'll get a warning about using an intrinsic, but there's actually, I think it's in standard memory. Size of a type, I32. So, and the other thing is that I don't actually need addition or casting to casting to integers to increment things. In fact, the authors of the standard library, not the standard library, maybe it was this, detected that this was a relatively common pattern of when you do have a pointer and you need to kind of do increments and offsets and so forth. And they thought, oh, you know what we should do is just add an API to safely offset your pointer so you don't need to do any of this yourself. And what I am interested in kind of investigating, or the kind of the research that went into this talk, looked at, given use of unsafe and then detection, can we detect other patterns that could be pushed into the standard library? Are there other things that we could make safe? There's another one, a couple of others actually, but this one is probably the best. So I've got one string and two variables, but I have a compiler error. What's gone wrong? The string is not copy, but that doesn't make any sense if you are on your first 20 minutes of Rust. Neither does we have moved the value. No, reasonable programming languages like a Python or a JavaScript, this is perfectly acceptable. So what has happened here is that, so we're technically correct, and this is the problem that we as people that go to Rust conferences have when we try to communicate with people that do not. We say things that are, they use English words, but they have such a technical meaning that they're just completely incomprehensible. String does not implement copy. And even if it did, we probably, so what this is meaning, so we create a second variable. The let keyword will shift ownership to B. Rust will refuse the access to A on line 5 because if we really intended to access A again, we need to re-borrow from B. And it's like, aha, but I had unsafe. And it's like, yeah, what I'm sort of saying is like, well, Rust, you think you know what you're talking about, but I wanted two variables. I really like having two variables. And sadly for me, the ownership rules still apply, even inside unsafe blocks. You do not get access to just kind of this crazy kind of free-for-all world. Unsafe is very limited in its capabilities. That's the big message. The idea is that, there's a couple of things. One, unsafe is not this kind of dangerous, crazy world. It is tractable. It is learnable. Secondly, you want to restrict the amount of cognitive complexity. You want to restrict the size of your unsafe blocks to the minimum amount possible so that you only need to verify the minimum number of blocks of code. Let me go back to my slides. The reason why I think that it's quite important to shrink unsafe blocks is because they're significantly easier to review. Here is an example. We've got a comment that says that the team member has asserted that current is sum. Therefore, by implication, this bump thing does the right thing. Okay, this is another instance of so we've created a box that is a trait object that implements error. And we are, for whatever reason, doing this with raw pointers. Okay. But it's conceptually understandable what's going on. And it's possible, though, you could argue that this is already too big. You don't need to use unsafe to create raw pointers. You only need unsafe when you actually go to either access them or dereference them. Here we have inline assembly, Inline assembly does require unsafe blocks, but you still get things like type safety. Rust will ensure that, also the Rust compiler will ensure that the right parameters are actually being sent in, and for example, the right bit widths to be able to satisfy the assembly. But this is pretty understandable if you read Intel or whichever flavor of assembly you prefer. We have an interaction here with the native operating system. It exports some library which defines its own string type. And so there needs to be an interface between the native library or something else, NS string, and Rust. Okay, I'm getting a bit boring, apologies. And then we get stuff like this. This is dangerous, in my view, because it's much harder to understand why someone has used an unsafe block around the whole thing. We want to ask Rust to do as much work as possible. Clippy is a better programmer than me. Thanks, Andre. And by the time we get to stuff like this, it's very hard to know sort of what's going on. So we kind of have this intuition that smaller is better, and we want very, very narrow use. And also, it's really nice to have documentation saying which invariants have been, so which preconditions have actually been already provided. Let me talk about some of the empirical research that I have done. It is in a repository, well, it will be in a repository that is in the very last slide. Turns out that there's this weird thing called open source, and we can just go and download every crate on crates.io. And every crate describes its own dependencies. So we have a graph of about 137,000 crates and about 700,000 edges in the graph. Oh, apologies for the typographical mistake. This is last-minute editing going badly. Of 300, so about 25,000 use unsafe blocks. And another 15 include that through their transitive dependency graph. So, okay, not too bad. Right? So essentially, if we were to audit everything, we would only need to audit, let's say, 25,000, which is, and then actually, it gets a little bit, or at least it seems to get a little bit better. Inside, 50% of those 15,000 actually use only 6 blocks in their whole thing. So that's okay. That's kind of auditable. But the 100th percentile is 79,000. When you start getting machine-generated code, and code that has been code generated from, let's say, C header files, compilers like Unsafe. It's very easy. And so most of this stuff is like, yes, kind of easy-ish, but yeah, 100% at 79,000 is kind of, oh, gosh. And there is actually one problem, though. So this is looking okay. But if Rust is a social organism or is a social network, one of the characteristics of a social network is that it obeys a power law distribution. A very small number of crates are extremely important. Therefore, of the now 59, nearly 60 billion downloads, only 4% have no unsafe in their dependency graph. This means that it is suddenly part of your responsibility as someone who is advocating for Rust at work to have a plan for saying, we know how to check. Because it's almost impossible for, I say almost impossible, you know, like 4%. It's not quite impossible, but it's very unlikely that you're free from unsafe. This is something that is present in your code even when it's not present in your code. I wish to introduce Cargo Vet. You don't need to go alone. A Cargo Vet is a tool which enables you to participate in a community of verifying specific versions of code. It's like, oh yeah, we've invested 3 hours of reviewing its 6 unsafe blocks, and we think it's okay. And you can essentially upload your report or submit a pull request into a GitHub repository, and other people can opt in to thinking that you are a credible person, and you, as the author of an application, are able to say that I have certain people that I trust and people that maybe I trust less. And then there is a little bit of tooling for it's not little, sorry. There is tooling for this audit process to be integrated into your build system. It's not perfect. It definitely relies on humans doing the right thing. And you should be skeptical. Because it's your business, literally, that it's your users that will pay the price for you deciding to just ignore things without consideration. And how do we do this? The top is the install instructions, and the bottom box is the usage instructions. So the cargo install, it's just a cargo subcommand, and inside your package, or inside your crate, you first need to provide some initialization, which will set up a configuration file which says, these are the people that I trust. Let's go have a look. That took a while. In this case, I actually am not really depending on anybody. My cargo.toml is exceptionally boring because I've just got a couple of snippets here. So I'm just going to cargo add Serde. Features derived. This will probably take about 4 years to download. Cargo vet. Oops. We didn't get a safe, we didn't actually pass. You need to do a little bit of work to tell the tool what you care about. And so this demonstrates that there is some work to do to say that for specific versions of my specific dependencies, I do trust them. But at least the tool is there. And then lastly, I also wish to introduce Miri. Miri is an interpreter for the medium representation or the internal representation within Rust. So it's sort of like and it's like, that sounds very, very abstract. Excuse me. Just sort of demonstrate how to install it. It's a little bit scary because it requires nightly. It is installed via ruststop. And here we are. Install nightly component Miri. Not every nightly has every tool installed, and so if you're doing this on the command line, sometimes it can just say, I don't have Miri today. There are various workarounds, but essentially the workaround is, okay, well maybe just go to yesterday's nightly. Or pick a specific version that you do care about. And now, later on, I can call cargo Miri test or cargo run, and your program will be run inside the Miri world, where it has full control over memory allocations and so forth, and we get a very interesting report. So allow me to look at the program that we just created, where I sort of said, yeah, of course it's unsafe. No, it's not. I can just use manual. Sorry. So here's our original program. And we wanted to check whether or not this use of unsafe, this block, we don't really know if our block B is safe. And we wish to verify this. So cargo plus nightly will ask for the nightly, sort of enable nightly features. We run, and then I have this binary A. There is a little bit of preparation. Mary kind of sets up its own environment. And then there is quite an extensive report. And it says, no, this is not safe. It actually does something that's a little bit better that I really want to show off, and that it is warning you that you are performing an operation. In this case, we are casting from an integer to a pointer that will decrease its ability to reason. So if you read through the garbage in front of you, you will see that this helpline in the middle, the implications of, implications of doing this, sorry, my computer is deciding to heat up, is that you may miss, if you cast from integers to pointers, Miri may miss bugs because it doesn't have the provenance information. So please use a different API. But here is the actual compiler error. It's that you have some undefined behavior during the deallocation. You're actually not pointing to the start of a span of memory that you care about. And therefore, Miri has guarded us against pushing unsafe code to production. This is a tool that you can integrate into your CI systems, and it will work through your, it will actually essentially push through your dependencies because it is running it against the compiled binary. And so you don't need to be an expert here, but you're able to give yourself a little bit of knowledge to at least put some guards in place to say, okay, let's check. And if there is a problem, well, we're going to need to ask for help. Or at least we file an issue. We do whatever we need to do to go to the next step. You go to my GitHub page, which is actually easiest to find. It's timclicks/tutorials. You'll find this on the Unpacking Unsafe repository, as well as these example code bases. And with that, I wish to say thank you very much for hosting me here. Hope this has been a really fun and enlightening talk. Cheers. Could we bring the house lights up, please? Any questions from the floor? Over on the right. You can call out and I'll just repeat it for the mic if you like. Oh, no, Tim's going. We need our steps in.
So with so much unsafe in the Rust ecosystem,
right,
is there like a worry, the US government's talking about we want memory safety. Is there a worry of drifting away from Rust because of the prevalence of unsafe, or is there kind of a pathway where that doesn't happen?
I'm going to say something which is intentionally antagonistic, and I apologize for that. What you get inside unsafe blocks is exactly what you get in 100% of code written in other languages that are of Rust's peers. Even shrinking, so of the 15,000 crates that use unsafe, that half of them only use 6 blocks, and probably, in fact, most of them are fewer than 4 lines of code. That's a huge step forward for the industry. Now, is it enough? Probably not. Have we gone and verified every single instance of unsafe in the whole of the open source ecosystem? Have we guaranteed that a maintainer of an important crate shifts and then someone just kind of subtly pushes an update? And then suddenly we've introduced a soundless hole inside, let's say, a third of the entire Rust ecosystem? No, we do not have guards for that. Nico's talk prior to this, which I'll actually make sure that I link to in the README of this repository, talks about some of the functionality that the Rust ecosystem is trying to address some of these supply chain security concerns. But essentially, Rust is still better, but it's just a programming language. It's a programming language operating that is providing an interface to a general purpose computer. General purpose computers do what they are told. And so, yeah, sorry, it's not perfect. But is this enough for, should Rust say, actually, so we should wait for 5 years to figure this out? No. Rust continues to grow rapidly because it is the best that we've got. We need, as a Rust community, and even if you feel like there's only 3 of us on the team, you can still submit a vet, like a patch, and say, actually, for this thing, we checked, and we're happy with it. That is a huge contribution because people that go to conferences are only such a tiny, small proportion of the overall Rust community. It's very, very large now. And so, yeah. Pleasure. Further questions at all? And down the front here, or towards the front. I'll try and change this.
Yeah, so we often say that like there's only a small number of, or you might look at a package and say there's only a small number of unsafe blocks, so that you think that makes the verification relatively easy. The thing I think is maybe not widely enough appreciated is that the tricky part with unsafe is that verifying what that does requires non-local reasoning.
Right.
So,
the
for
whole
example,
point is that you need to know the whole program in order to actually go and verify those 3 lines.
Yeah. So in your example earlier, the unsafe block had to go around dereferencing the pointer, but in order to prove that's safe, you need to know all the history of where that pointer came from. And
maybe I stressed that too much. I agree with you. The intuition was that these smaller, more constrained unsafe blocks are easier to grasp. But I think the point that you're making is absolutely correct. That in order it's still quite hard. You need to know where the memory came from. You need to guarantee that there is only a unique part of the program where destruction will occur, and you need to verify Rust's aliasing rules. And so there's and that could essentially occur anywhere in the program. So, no, I agree. Oh, right at the back, we've got a waiver. Sorry, Andre.
So you said that only a portion of the crates depend on unsafe, and it's a big portion, but still a portion. But that's not true, because all crates depend on unsafe because standard library has unsafe. And while the standard library developers obviously know what they're doing, they can make bugs in unsafe too, and we did this a lot of times. So, yeah, what's the point on...
Okay, so the argument was... The standard library includes, there's a question down here, hopefully I'll get the timing right. The standard library, by design, requires unsafe. It interacts with APIs which have essentially sort of nightly features of the compiler which have been designated as never stabilizing. So unsafe is required. And the version of the standard library works with the version of the compiler. And in fact, to compile the standard library, the stable version of the compiler needs to be tricked into enabling nightly features. So the job is not done with the third-party ecosystem. It means that in fact, the first place to verify that things are going well is the standard library. The tools that we've talked about, and particularly Miri, will also do that verification, at least within the aspect of the API that you're using. Now, it's very, very hard. So this just culturally, it's like the standard library maintainers must be expert Rust programmers. They are just humans under pressure. Just like you are a person under pressure writing software. Writing software is very difficult. These are not superhuman beings. The standard library maintainers will love your help. It is very intimidating it takes a lot of courage to participate in something as large as a Rust project. You need to install new tools, you need to have a whole bunch of communication styles that are probably brand new. But if you have a desire to contribute, please do.
So first, thanks Tim for this excellent talk. And one thing I want to mention is that basically the rules for sound use of unsafe are also a bit in flux, and some will even say that whatever the standard library does is probably okay. So there's a bit of a chicken and egg problem.
That is a very interesting point, that actually it looks like everyone's kind of figuring this out. And the centrality of the standard library is it impacts the rest of the ecosystem. For example, result and option seem like they're essential to Rust. But the Rust compiler doesn't know what a result is. The Rust compiler does not know what option is. These are types which are introduced by the standard library. The standard library is so critical to what it feels like to be a Rust programmer that we sometimes forget that they're separate.
And the question I wanted to ask is, how do you make sure that Miri actually checks your unsafe code? Because, well, it doesn't exactly need to be called.
Okay, so Miri has several caveats. If your code doesn't actually interact with the unsafe blocks that you want to verify, if the code paths don't match up, it's like code coverage of all the branches. If you haven't got a code path that Miri follows, it won't verify that you have upheld the invariance that you're required to. There's a question further on towards in the middle over here.
Hi, thanks for the talk. Is Miri capable of, the sort of, when you're writing an application and you're referencing these libraries, the library might have a tiny piece of unsafe Rust that you're not even using. Is there some sort of analysis that you can run to see if, static analysis, that at least that you can see that you're actually hitting any form of unsafe code?
There are
using Miri or something.
So there are tools emerging. I think if we have this talk if there was a similar talk in, say, 2 years' time, the situation would be different. That, in fact, there are static analyzers that can introspect much more. I am not a Miri developer. And so I'm actually unsure of exactly I'm at the edge of my knowledge here. So I don't know exactly where the boundaries are, except to say that there are caveats that are well documented, and it seems to me that the Miri ethos is to avoid false positives, which is it tries not to say that this will be a problem when it isn't. However, it accepts that there may be false negatives. That is, some code will pass that shouldn't pass. And again, so it's an incomplete story. Further questions?
Hey, Tim, I have a question about sort of practical usage of Cargo Vet. You know, let's say you're a developer who wanted to use Actix Web and wanted to know whether I should add that to my sort of vet config file. Do I trust this crate? And maybe you don't know how to even go through that probably massive crate and review all its unsafe or run Miri in all the correct ways. I guess it's sort of possibly two questions, like how do you, as a library maintainer, show that you are worth trusting and like show what you've done to verify these things, and how as a developer potentially taking on these dependencies validate that a person might be trustworthy?
As someone that might be just writing a thing, you probably exist within a community. Like, for example, it's like, oh, I want to write a Leptos app. Well, there's probably people in the Leptos ecosystem that I can call on. If I'm writing such a, and so my recommendation would be to reach out to the community of people that you know, and start incrementally. Don't feel as though you need to start with Everest. You can start climbing, you can start with you don't need to go for the hardest task and complete 100%. You can get there eventually. Because at the moment, even having an awareness that this is a problem places you so significantly ahead of sort of, what you had before the start of the talk. That it's just a process. Again, this is, and in terms of if I was a library author, how do I increase the likelihood that someone will vet the safety of my crate? There's a lot of sort of hygiene related to developing libraries, like decent documentation, trying to be very clear around API stability, a lot of responsiveness to issues, and being able to accept criticism or being able to accept external suggestions for features. It's a human kind of problem about being perceived as trustworthy. And Rust is, again, Cargo Vet is another incomplete solution. And the other things, like if you need Unsafe because you are literally interfacing with a microcontroller and you want your hardware abstraction layer, add a syscrate and then provide make sure that you're kind of following standard conventions. There is another question just down through there. Hopefully I've been,
You're good, you're good.
I'll say.
Thanks for the great talk, fellow Kiwi here. I have a question about beginners who actually go the other way with Unsafe. So I've seen like a C developer, for example, say like, I need to get my circular buffer running, I can't figure out how to do it in safe code, going straight to Unsafe. How do you kind of guide them from there?
Yeah, I've seen a really funny meme. I was actually going to put it in a slide, or as a slide, just be like, you get really itchy. Because it's like, Rust feels extremely frustrating, and I really just want it to work. I know that the pointers are okay. Just let me. It's a process. No. The process of moving from one language, one paradigm to another, and trusting the Rust compiler, and start. It's very, very difficult because as soon as you tell someone, no, the practices that you have been doing for the last 15 years, a lot of the time cause very significant problems. That feels very threatening. Suddenly you're telling someone who feels, they have actually created their identity around, let's say, being a C++ developer. I am well known in my local, I've done user groups, might have even published big things. And suddenly you're telling them, no. That's it is a cultural shift. And so I think the thing to recognize if you have someone who might be particularly kind of frosty and kind of feeling a little bit agitated because it's kind of annoying. I just want my doubly linked list. This is what my first year of university, I implemented a doubly linked list in C, and this was like the second assignment that I did. But can Rust do it? No. Okay, but there is going to be, unfortunately, there's more than one person, so I can't give a universal answer to that. Just kind of accept where people are. They will think about it, and as soon as they don't have to figure out these memory safety issues, no one wants to find the hole. It's like, well, where did this pointer come from? I don't even know. There's a question just here.
This will be the last question before we go on break.
It's been a really, really enlightening discussion. Thank you so much for everyone, by the way. Hopefully I've been mostly reasonable.
Yeah. Right. You've looked at looks like you've looked at like unsafe blocks throughout the ecosystem, and it's touching on best practices certainly. Like best practices, don't use unsafe if you don't need it. So you're counting how many unsafe blocks there are. You're mentioning small unsafe blocks, which, in my opinion, like one thing you clearly demonstrate there with the large unsafe blocks, it's hard to even find the actual unsafe operations in there, and the non-local kind of stuff can hardly be avoided. Where, on the other hand, I liked the example that created the pointer and that was still small enough. Anyways, there's more best practices, like for example, one good practice is to comment the unsafe blocks and to explain in the code why they're safe. Like the great author is the first one that's supposed to vet their own unsafe blocks, look at them again and document it. Is there like, maybe it's hard to measure automatically, but like, are there unsafe blocks in the ecosystem mostly uncommented or mostly well explained or something in between?
So I went down thank you very much for the contribution. I think there are good practices. The methodology for this is all actually going to be open access as well. I have, it should be fully reproducible. Part of it uses AST grep, so we can actually go, it wasn't just like me looking at text tokens. We kind of used a little, some good baby compiler to actually go and extract these unsafe blocks to kind of do some analysis. But it really only touched the surface. And I was looking for this exact thing. Give me the number of unsafe blocks that are preceded by a comment that includes the word safety. You can actually ask the tools to tell you that. And the problem is that there's no end to these types of questions. And, I was looking for, are there patterns that could be pushed into the standard library? Just like incrementing or offsets, for example. We no longer need to do that with manual conversion or casting to integers. This is kind of no longer necessary. But I ended up getting stuck with, okay, I've got tokens and now I need to fully resolve paths, and I don't have any type information because I'm just working with syntax trees, and I got a bit lost. So if there is anyone who would like to contribute to fleshing out this project, I am actively looking for partners, I think, in the academic community to host PhD students. I'm hopeful that my consultancy can actually maybe fund a PhD student position to kind of really put this to work. Thanks very much, Ernest.
Thank you very much, but don't... We're gonna have a lot more Tim, because Tim is coming to save the day. Walter, unfortunately, has caught COVID, so his talk on Painter won't be happening today because of obvious reasons. So Tim is going to step in and fill that slot. So that will be later on in the afternoon at 2:45. So if you want more Tim McNamara in the King Vault, you can go down and see his second talk there as well. So please give him a massive hand. All right, we're now going to have a refreshment break, so thank you. This is happening. Well, it is. Good. How you doing, Mark? You all right? You met Tim? All right. Nice to meet Make a big step forward. Are able to pay the money. We're gonna have something. In around the logistics, like once we get that sorted. Thank you so much.
Months or so.
Yes.
To find somebody.
Yes.
Because we have the next one aligned.
So what we'll do, what I'm trying to do, sorry. Okay, hello everyone. Welcome back from the break. Please welcome Pietro Albini. Give him a massive hand.
Hi everyone. Safety critical is everywhere around us, even though we might not notice it. Because we have, software is permeating all aspects of our lives. And we are also noticing that some places, if software goes wrong, people might actually get hurt. Thinking like cars, the software that controls the brakes. Thinking like airplanes, medical devices that let people with certain conditions continue to live. And because if you have your mobile application that delivers food, for example, if the application stops working, it's not such a big problem. But if instead you get to a car and the brakes stop working, that is way more serious. And that's what safety critical is. Safety criticals are, or functional safety, are all of the systems that where a failure could harm a human life, where something going wrong could be catastrophic. And it's actually one of the few parts of our sector that are regulated. It's, programming is quite weird because anyone can do it. While if we compare to any other engineering area, there are state exams, there are certifications that we need to have. And safety critical software is the only place in software where that is present. And one crucial thing about safety critical is that it requires qualified tools. You cannot just use any off-the-shelf compiler. And one of those tools is a qualified compiler. And that's what we built at Fero Systems. We created FeroSym, which is a qualified compiler for Rust. And in this talk, I want to go a bit on what does it take to qualify a compiler? What does it mean for something to be qualified or certified for safety critical? And what is the process? Because I think that it's something that everyone has a vague intuition of yeah, it should be safe, it should not have bugs, but what does it take in practice? So hi, I'm Pietro. I am the technical lead of Fero Systems for FeroSym. And I'm also a bit less nowadays, but I'm also involved in the Rust project. So I'm part of infrastructure, release, and security teams. And also previously I was on the Rust core team, and I led the infrastructure team before JD, who spoke earlier at the conference. So let's start. What is safety critical? I kind of mentioned it already before, but safety critical is any system where any malfunction could actually harm a human life. And there are a lot of areas that are safety critical. And crucially, each of those areas have some regulations for what you have to do to get your software qualified and certified for safety critical. And all of these are kind of the same in the sense that the general principles of all of these standards for the various areas in the industry are kind of pushing in the same direction, but each of them have slight differences on how they call stuff, on some requirements that are specific to that environment. Each of the standards, unfortunately, most of them are paid. You cannot actually go and buy and read them without buying them. And they are they're not actually that boring. Because a thing that safety standards do is that they don't prescribe what you have to do. You're never going to find in a safety standard for safety critical, you actually need to use this technology in this piece of software or do this in this specific process. What they do is they tell you what the goal that you should achieve, what is why and what you need to do something. For example, an example I always like to make is no safety standard actually tells you you have to use Git or you have to use a version control. What they may tell you is you have to have processes in place so that you can track changes and who made those changes. And if your approach is to have your developers fax the difference to a notary to be notarized every single time, that totally works for safety critical. You probably don't want to do it, and you probably just want to use Git. But you just have to figure out a procedure that works for you and works for your project, and document it and follow it. Another really important thing to think about is the difference between qualification and certification. Because those are terms that I often see used interchangeably, but they're actually very different because certification is for what actually goes into the safety critical system. So for example, what goes into the car, what goes into the plane. While qualified tools are used to produce the certified software. And it's a bit weird because qualified tools are never mentioned in, for example, the automotive standards. And you can build your safety critical software without using any qualified tool. Because what actually the standard mandates, and that gives back to the thing I mentioned before of the standard never say the exact procedures you need to follow. The standards want you to review what goes into the safety critical system. So in this example, we have some schema, for example, for a remote procedural call protocol that goes for a generator to output source code that then goes into the compiler that gives you the executable or the library. And the standard says that you need to review what goes into the system. So if you take it literally, it means that you have to manually review the executable that goes into the car, which means manually reviewing the assembly generated by the compiler. And nobody wants to do that because we are our time and not wanting to spend weeks just reviewing a single module. What qualified tools do is they move the bar where review has to be done. So for example, if you take a qualified compiler, the review is moved to the source code. So you have to review that the source code does what you want, do all the verification that is required for certification and all of that. But since you use a qualified compiler, the output of the compiler is assumed to be good. It's assumed to be that the compiler correctly translates the source code into the executable you want. And it doesn't miscompile something. And if you wanted to go also further, you could qualify the code generator you use. So that you don't even have to review the source code that is generated. If you have both tools qualified and they speak the same language, then you just need to review the high-level schema. And which level to qualify and how many qualified tools you want to use is often a business decision. Because qualification is quite expensive. It takes a lot of resources to do. And it's quite expensive. And so it almost always makes sense to use a qualified compiler because nobody wants to review assembly. But if the output of the code generator is fairly readable, it might not make sense to go through the trouble of qualifying it. And so you might just want to say, the schema can be whatever, what we review is the source code. But what does it actually mean for a tool to be qualified? And for context, in the rest of the talk, I'm going to cover only qualification, not certification. What tool being qualified doesn't mean that it doesn't have bugs. Because you cannot write a program that doesn't have any bugs. If someone can figure out how to do it, let's revolutionize the industry. It's not possible. What it means is that you have done your due diligence to prevent bugs from happening. You must have done enough and done the best you can to ensure that it's rare that bugs sneak in. And also, the other important part is quality management. So what do you do if a bug sneaks in? What are our processes for developing to ensuring that there are no bugs in the resulting software? And quality management is a fancy word for saying that you must have the processes in place in your company to guarantee that quality, and you must follow them. And that brings me to Ferrocin. Ferrocin, which is the thing TTS Systems has been working on for years now, and is the first qualified Rust compiler. And it's currently qualified for automotive and industrial safety to the highest level of assurance, which means that now you actually have a qualified compiler to be able to write in your Rust the software that powers the brakes of your car, the airbags of your car, like those systems that absolutely have to work. And thanks to Ferrocin, Rust is now a valid language to use in those contexts. And a thing I really like about Ferrocin is that it's fully open source. The safety critical industry, especially for tool chains, is very rooted into the old proprietary, extremely expensive tools. But for Ferrocin, we wanted to kind of bring some of Rust's magic into safety critical, not just the language, but also the ecosystem, the way things are developed. And having everything open source includes having all of the documentations that we are producing be open source. All the documentations that we are then going to send to the assessors to verify. And as far as I'm aware, this is actually the first in the industry. You might have compilers that are open source, mostly because they're based on GCC and thus have to provide you the source code, but nobody before us actually published the qualification documents. And so that's kind of what I want to do in the talk. Let's go through them. Let's actually see what does it take to qualify a compiler. All of the steps that we have to take to go from the upstream compiler that you all love and use to something that is used in the automotive industry, for example. And a disclaimer, there is very little boilerplate. And this was actually something that surprised me when I joined Ferrocin, because I didn't have any previous experience with safety critical. I was working on the Rust project on the infrastructure, making sure that you can download Rust. And, but there's actually very little boilerplate. There are very few pieces of documentation that are just present for the sake of it, for the sake of documentation. And most of that has an actual practical use. And so we can go into the first step, which is the evaluation. So doing an analysis on the software you're about to qualify and figure out exactly how much work do you need to do to qualify, what are the steps you need to take. Because I will see later, it's vastly different depending on the software and the impact the software can be. There are very different amount of steps to take. And again, as I said before, the standards don't prescribe that you need to have an evaluation and how you structure it. The way we chose to structure it is to split it into two documents. We have the evaluation plan, where we describe all of the processes that we take. So how are we going to do this evaluation? And then we have the evaluation report, which contains the outcome. So what did we find during the evaluation, and what is the result? What steps do we need to take next? And the first step of the evaluation for us was defining the use cases. How can you use Ferrocin? And this is not a pointless effort. It's going to be useful later. And for Ferrocin, we actually found 4 use cases. Because it's a compiler. You of course need to install it, and then you use it to build a project, a library, a program, an executable. And this effort is useful for the next phase, which is how can the software fail? What are the ways that the tool can introduce a bug, can result in the code that it generates not being what you expected? And having a list of use cases is actually fairly useful for that, because you might not think of considering installing Ferrocin as a use case, but having that as a use case and having to figure out the failures of that for example, allows you to figure out, hey, a failure possibility could be if you mix files from different ferrocene releases, what would happen then? And for us, the way we do this analysis is through what we call the hazard and operability study, or HAZOP, as I'm going to call it later. And the HAZOP is basically sitting down and trying to figure out all of the possible ways the software could fail. And writing them down, we chose to just write them down in Google Sheets. And so we had a huge table of all of the possible ways it could fail, and some of them, like these ones highlighted in green at the top, were things that we thought it was a possible failure, but in practice it wasn't. Like, there was no way for that failure case to happen. And there are instead some possible failure cases that are indeed possible, and we need to figure out how to prevent them, how to make sure that they don't happen when users use our safety critical compiler. Which brings me to the next step, which is how can those failures be addressed? And again, this is all analysis. This is just ahead of time trying to figure out what work we want to do. And there are actually two ways to figure out the possible ways software to address those failures. One of them is through testing, is to write tests, reuse tests that exercise that part of the compiler and that verify that that failure is not likely to happen. And of course, this doesn't guarantee that it's never going to happen, because in software, the test suite there might be a corner case missed by the test suite. There might be a bug we didn't anticipate. But there is also another option, which is to just tell the user they need to manually do something, to constrain through documentation how the user can use the tool. And I'm going to go a bit more into how that looks later down in the talk. But having those two options mean we have two ways to prevent the failures. And for each of the failures we identified in the HAZOP, we then had to figure out, first one, how is that preventable? And so now we did all of these analyses. We knew exactly how we wanted our users to use the software, how it could fail, and how we can prevent it. And we needed now just the last step of the evaluation, because it's figuring out how much work do we actually need to do for the qualification. And I'll actually use the automotive terminology for the rest of the presentation, because a fairly annoying thing is that every single standard calls things differently, in the sense that one standard might call safety level 1 to 4, and another standard might call the same 4 to 1, or A to C. Like, it's extremely inconsistent. I'll just speak the automotive terminology. First, we need to figure out where we expect our software to live. Because the software that powers the air conditioning of the car has vastly different safety requirements than the software that allows to trigger airbags. Like, if the air conditioning doesn't work, it's going to be an unpleasant car trip. If the airbags doesn't work, let's not talk about that. And depending on this level, which is in automotive is called ASIL, so for automotive safety integrity level, it can go from A to C to D. And usually, users of the compiler just pick the one that their product will go towards. For first thing, we are kind of forced to go for ASIL D, so the highest level of assurance, because for us, it meant that the compiler could be used anywhere. And then we need to figure out, what is the tool impact? Can the tool introduce errors? Can those errors be missed? And then it's a simple answer. No, like, there is no way that the tool could cause a failure or an error in the resulting code. For example, add inter. Add inter is probably not going to cause a failure. Or yes, like a compiler could introduce a miscompilation. And the other thing we need to determine is how likely it is that those errors can be detected. How likely it is that a user could detect something is wrong. And for a compiler, it's really hard, because if a compiler produces the wrong machine code, unless your test catches it, good luck figuring that out. And then you just plug everything into a matrix. And you see that if the tool integrity is 1, so that the tool cannot impact the safety of the overall system, then it's always the highest confidence level. And so that will mean we have to do less work to qualify. While if it's TI2, so it can impact the safety of the system, then we might have to do more work depending on how likely it is that an error could be detected. For example, Rust-C, the compiler, is TCL-free, because it's possible for the compiler to affect the safety of the overall system, and it's really hard to detect miscompilations. But it's not always TCL-free. For example, let's take Rust format. And to be clear, this is provisional. We haven't, while for Rust it's approved by the assessors, this is our current in-progress analysis. But Rust format can definitely impact the safety of the system, because if when you run Rust format, it outputs some code that doesn't have the same meaning as before, it will impact the overall system. But it's really easy to detect if Rust format did something wrong. You just have to review the code it generates. You just use Rust format in a repository that has version control, and you check the diff of it. And so that is TCL1. And as I said, this determines the scope of work. So in automotive, TCL1 doesn't require qualification. And that's why it's important to do the evaluation, because if possible, you don't want to spend a year or two going through the qualification process if you can avoid it. And with this, for example, for ferrocene, we identified that ferrocene is TCL-free. It has the highest level of risk, and thus we need to do qualification. And now I need to drink something if you want to listen for the rest of the talk. Let's go next. Let's start with the actual qualification. And the first thing is writing requirements and testing them. So in short, figuring out what is our software actually supposed to do, how it's supposed to behave, and ensuring that we have enough test coverage that we are verifying all of these use cases. And for a compiler, it's actually both simple and hard, because realistically, apart from a few requirements on the command line interface, the bulk of the requirements of a compiler are the language specification. What is the compiler supposed to do with the input you give? What programs are accepted and how they should be converted? And it's easy because you just have the language specification, but it was hard because there was no unified and complete Rust specification. There were efforts like the Rust reference, but they were not complete. And so what we did is we just created one. We sat down and we spent around 6 months, I think, with a few full-time people working on it. And we went through everything, and we wrote the first language specification. To be clear, it's not the official specification of the Rust programming language, because that's something that the Rust project is actually working on right now. We have Mara at the conference, who is on the team working on the specification. And this is not something official. This is just our requirements document that we use for our purposes. And we decided to publish it in open source if you find it useful for your own purposes. And as a quick aside, because this is just a fun anecdote, the whole language specification was actually written in Google Docs. So we had a very weird and very long Google Docs documents where we basically created a dialect where, for example, different fonts meant different things, words highlighted in yellow were going to be turned into links. We had one bookmark for every single paragraph, except for one time when a script went wrong and created 100,000 bookmarks in a document, and the document was really slow to use. But why did we do that way? Why didn't we just use GitHub and put markdown files or restructured text files in a Git repository? Well, because you really have to use the best tool for the job. And for us, working on a large technical document, Google Docs was actually the best choice, because it allowed us to be able to quickly comment and suggest fixes all across the document. I think that I have never used a system that provides real-time comments and suggestions as good as Google Docs. And so this is just a small aside of using Git and having everything done through GitHub is not always the best tool for the job. And make sure that you consider the requirements you have for what your tooling wants to do before committing to a choice. But now we had, 6 months later, we had a full language specification. And now we needed to ensure that we actually tested it, ensuring that every single section of the specification had some tests that proved it was correct. The way we did it is that we had every single section of the FLS had random IDs. They were random because that way they were static even though the content might change, so we didn't have to redo the test annotations. And then we went through the entire Rust upstream test suite, and we added comments linking the annotations. And here I actually want to give a shout out to the Rust project as a whole, because we actually didn't have to write any test, practically. We had a few of them, but the Rust test suite was good enough that it was able to cover all of the language and all of the language specification. And so at that point, we had a full list of requirements, a whole test suite with annotations, and we needed to merge it together through the traceability matrix. And the traceability matrix is a document that shows that merges the two information together, and for every single section, ensures that you have the good test coverage. So this is the actual traceability matrix for Ferrocin. And it's a very large and heavy page, because in addition to the summary, for each individual test, for each individual section, it links all of the tests in the Rust test suite that cover that part of the language. And this was a very boring manual effort to go through all of the tests and categorize them. And this is, in the end, what we give to our assessors, how we can prove that we have the confidence that the bugs are not likely to be there. Because, let's be frank, Ferrocin already has bugs. Ferrocin are going to have bugs. And it's impossible to prevent all of them. But this showed that we did our best, so we did our due diligence to ensure those bugs are not present. And again, nothing in the standards say you have to do a traceability matrix. This was our process. If your company and you want to qualify another tool works best with a different process, just document it for the assessors. And then we dive into the last part of what does it take to qualify a compiler, which is the quality management. And quality management is described in our qualification plan, and it describes all of the processes we follow. And crucially, quality management is not something you can sprinkle on the project at the end. It's not a layer of paint to add to it. It's the whole development cycle. It starts from what do we want, planning what do we want to do, to implementing it, to building it, testing, shipping it to customers, and how do you support customers afterwards. It's all of the documentation, it documents all of the processes, and actually having them written down is good. And it doesn't have to be enterprisey, very paperwork-heavy process. You define the processes. The standard don't mandate anything. I'm repeating that a lot in the talk. And for us, we said, let's get inspired by Rust. Let's not just use the Rust compiler, but also use their development practices. And there are two reasons why we did that. One is that Rust practices are actually very good. Rust is one of the open source compilers with the best quality management all around. And that is proven by the fact that Rust can ship new releases every 6 weeks with very little regressions. And also, a lot of employees of TTS Systems are former members of the Rust project, so this was the process that was familiar for us. This was the process that worked for us. And for the development, the easy answer is that we need to have mandatory code reviews for everything, and we use merge queues to test changes. Merge queues in the Rust ecosystem are also called bors, which is the name of the bot we use. And this comes from Graydon Hoare, the original creator of Rust, rule of the not rocket science rule of software engineering, which is to automatically maintain a repository of code that always passes all the tests. And as an aside, I cannot wait for Ferrocin to be qualified for aerospace use, because then we'll be able to say that finally the not rocket science rule will be qualified for literal rocket science. In practice, we use BorsNG as the merge queue, which was our implementation of Bors in Elixir done by a member of the Rust community, which right now the public instance has been retired, but we continue maintaining our own private instance of it. And what BorsNG does is it takes care of testing and merging one pull request at a time, or at least a group of pull requests at a time. Because even if a pull request passes CI, it doesn't mean that it won't break when you merge it to the main branch. Let's take a very quick example. You have in the main branch a commit that does that drive function, and that passes tests. And then you create two pull requests. One pull request adds a new place that calls the drive function, because it's useful. But then another developer realizes the function is not the correct implementation, and in another pull request removes it, and removes all of the places that call it. In isolation, those two pull requests are good, because when you take them with the main branch, they pass all the tests, they compile. But if you try to merge both of them into the main branch, you will result in a broken book, in a main branch that will fail the tests, because at some point you will have removed the drive function, but you have a place that calls it that you didn't remove in the original pull request, because it wasn't on mine yet. The merge queues solve this by testing one pull request at a time and testing it with the current main branch. So what it means is that you put both pull requests in a queue, and the bot will only first test the first one. And it sees that it passes the tests because adding a new call to the drive function works when the drive function is in main. But then, so the bot merges it into the main branch. But then it tries to build the new one, and it tests the merge commit of the new main branch, the one we just created with the latest merge, and the PR we want to test. And there the bot sees that that it will fail, and it doesn't merge it. Using a merge queue is great when you have a repository with a lot of activity from a lot of developers, because it prevents the main branch from ever being broken. And I personally also find it useful in projects I'm developing alone, because if you have a long-running pull request based on an old copy of the main branch, CI on at least most of the public CI systems available only test pull requests with the old main branch they were built on, based on, rather than the latest one, and so it really helps with software quality. And also another thing we take inspiration from the Rust project on is that we run all of the tests and build a full release for every single pull request we merge, regardless of what pull request changes, because we might have a pull request that includes so many new things that, of course, it needs to be fully tested. But there might be a pull request that just fixes a typo in the documentation. With our approach, we still run the full test suite across all of the architectures we support, and we build a full release for all of our targets for that type of fix. This is actually good, even though it's on some sense it's fairly wasteful, because we are running tests that if you just fix a typo in the documentation is not going to matter, not going to cause tests to fail. But this prevents whole classes of failure when your dependency tracking that checks which tests to run depending on which chains fail and don't detect that they must have actually run the tests. And so it makes, it also improves the main branch from always being green. But also it aids how we do releases, because now we don't have a separate build process for releases that could fail, because releases are built as part of CI, and if building the release fails, it's not going to get merged. And so our release process in the end is basically a glorified copy and paste, because it just takes the release that was built by CI for the latest commit and publishes it. In general, all of the, as I said before, all of the processes are documented. This is just a quick overview of the ones I think are the most important, but I don't want this talk to be Pietro reads the Ferrocin qualification documents aloud. If you want to learn more about our processes, they're all publicly documented. And this is our processes. Now we go to the second to last document, which is the qualification report, which is actually fairly simple. It's just a table of the tests we executed. It's the summary that gives to the assessors the proof that we ran all of the tests we claim to run, that all of them were linked, and that we followed our processes. And I want to also go into a quick aside here on how did we run the tests on the bare metal target, because Rust, of course, supports running in an environment where you have an operative system, like where you have Linux, for example. But it also supports embedded targets, no STD targets, that we call bare metal. For example, Ferrocin supports the ARM V8A bare metal target. But how do you run the tests? Because the Rust test suite actually depends on having the STD crate available. It wants an operating system to run. And honestly, it's just not worth it to try to change, because Rust test suite right now is around 20,000 tests, and reverting all of them to be running in an embedded system is too much work. So we cheated, in a sense, because the advantage we have is that we control the compiler. And so we created a new target that we're not distributing to customers, because it's just an internal thing for testing, that has the same configuration as the bare metal platform, but has the standard library enabled for Linux. Because in Rust, a good design of Rust is that all of the APIs that depend on the operating systems are part of the STD crate. And you don't ship the STD crate in a bare metal target. So we created this weird target that had STD for Linux, but it was on bare metal. And this way, we are able to easily and reliably run the tests for the bare metal targets that we ship. So many tests were broken. Like, I'm pretty sure we are the first people actually doing it, just for the sheer amount of failures we had to fix. And all of the fixes we upstreamed, so we sent pull requests to the Rust project to fix those. And so if you want to try that now, it's more feasible. But yeah, that's how we tested bare metal targets, which was one of the biggest challenges we had to face for Ferrocin. And so we get to the last document, the safety manual. What ties everything together? The document that we give to our customers for how to safely use Ferrocin. And this document is fascinating, because it's something that I want in every single industry, because it's a piece of documentation that customers are legally required to read and understand. Like, imagine writing your software documentation and your customers being legally liable if they don't read it. It's awesome. And because the safety manual describes the constraints customers have to follow, which is what I was mentioning before at the starting the evaluation report. Like, we can say, you have to do something to be able to safely use Ferrocin. We could say now in our safety manual, you have to manually review all the assembly. We wouldn't sell a copy of Ferrocin because people will go to our competitors. But if there is, for example, a soundness issue in Rust, because there are a fair amount of soundness bugs present in the standard library, you can just write guidance on how to avoid them. If you cannot write a fix yet because they might require larger factorings of how the type system works, you can just say to customers, don't write this code pattern and manually check that you're not writing this code pattern. We can defer checks and defer fixes to our customers. And it's something that we want to keep extremely low because, again, it's manual work for our customers, and if we have too many of them, customers are going to go to a competitor. But these are key advantages in how we are able to maintain safety. Which brings me to the last thing, which is the known problems. What bugs are we currently know of in Ferrocin? And even here, instead of fixing them, we can provide guidance on how to avoid them, and customers are legally required to follow it if they want the qualification to hold. This one is actually the only part of Ferrocin that is private, mostly for logistical reasons, because if a customer shares a sample code that exercises a bug, they probably don't want us to publish it and open source it on the internet if you're thinking about large automotive customers. But for Ferrocin right now, the known problems are just a curated collection of the upstream soundness issues. So there is nothing secret. There are no secret Rust bugs that only we know of. And that's it. This is all of what it takes to qualify a compiler. Now you just need to take it and build all of the documentation together and send it to an assessor to review. In our case, we use TUVSUD, which you see this logo everywhere, like if you actually start to look for it. And so TUV took our documents, reviewed them. We had a few review cycles where we gave the documents, we had a few review cycles where they gave some feedback, we fixed it, and so on until it was good for them. And they gave us the shiny stamp that we can now use in conference talks, for example. And we were very careful to make sure that qualifying new versions of RC is not going to be hard. All of the processes we've done are there. Like, they're not going to change. Like, we can change them if you want to, but we already have processes that work for us. Rust releases are really small nowadays. Like, you see that there are some releases that have a lot of features and some releases that, as a member of the Rust release team, as part of my volunteer tasks, I don't even know what to put in the announcement blog post because there's nothing notable in the new release. So it's not hard to update the test suite and the language specification to cover the new releases. And also, we heavily invested in automation. We don't need Rust to slow down to be used in safety critical. If we take an approach that is taken by a lot of the legacy compiler, safety critical compiler vendors, yes, maybe, but we tried really hard to make sure that we can bring new energy into the safety critical system, in addition to a new language, that we can make sure that we can deliver a qualified version for the highest level of assurance with fast release cycles. One of the ways we do that is we pull new changes from upstream as fast as possible. We have a daily job that opens a pull request with everything that changes. And usually, we are not far behind upstream. This is way better than basing off an old version and then every few months having to rebase over the new version of Rust, because there might be not that many surface changes to the language, but the Rust compiler gets heavily refactored all of the time. So if you ever maintain a Rust fork, you know how hard it is to keep up and stay up to date. Ferrocin is usually just a day or two behind upstream. We have, in addition to our qualified channels, we have our channels that are automatically published that track Rust nightly, beta, and stable. And usually nightly just a few days behind. Stable is often released the same day or close to the next day. And this is all thanks to the automation and our desire not to slow down Rust and Rust release cycle. This was not just my effort. I was one of the first employees of Ferrocin Systems working on Ferrocin, but there were a lot of colleagues of me at the company, and also external collaborators that we had the pleasure to work with in the past. And so thank them. Don't thank just me for bringing Rust to safety critical. And that's it. Again, this is just for qualification of the compiler. Certifying programs that go into a safety critical system is way harder. And for example, the next thing we're working on at TTS Systems is certifying libcore, so that you can start using Rust without having to do the certification of core yourself. But I think these processes could be useful for anyone in all other industries. Like, you don't have to actually do the matrix to figure out what the tool impact is, but none of these processes are like bureaucracy for the sake of bureaucracy. They're actually fairly good ways to improve the quality of your software. And so the big takeaway I take from working for the past few years on safety critical is that there is a good reason why these processes are in place. Of course, a good reason for safety critical because a lot of the standards are, frankly, written in blood. A lot of what is in the standards was explicitly written there to prevent a crash, a failure that harmed people in the past. But you don't have to, if you work on a mobile application, a web backend, you don't have to follow them to the letter. But a lot of these processes might help you make your software better. And so thank you for listening. And I hope this was insightful and shed a bit of light into the world of safety critical. I don't know whether we have time for questions or, okay, awesome. I see some hands.
Thanks for the talk. I was curious about the ongoing efforts that you mentioned to keep up to date with the Rust compiler. Like when you pull out new updates every day, what does that actually look like in terms of what you have to update in the spec? Like do you have to go categorize new tests to say what they exercise or what else goes on there? Okay, so when I said staying current with upstream, I mostly meant like with actual code changes. Usually what we do is when we decide which version do you want to ship as the next qualified version, we then go and do the work to update the specification and include new features and make sure tests are linked. That is something that, as I said, Rust doesn't change much, so that is very quick to do. The big problem about staying up to date with the Rust compiler is that if you depend on any internal API of the Rust compiler, in 6 months, it's probably going to break, whatever the API is. Because the Rust compiler teams does a lot of great effort of refactoring, for example, to improve performance. There are not like very fast, like there are no groundbreaking improvements in Rust performance, but if you look at the graphs, it's constantly getting 5% faster release over release. And all of that requires refactoring and requires a lot of code changes. And so that's why you want to keep your code base up to date. What it looks like, it's a pull request that is opened by automation. If you go on the first in your repository, you can see countless of them.
Thank you for a great talk. Can you dive a bit more into how you tested into how you run the test on the bare metal? So you said that you include the version of STD for Linux, but I mean on the bare metal there are still no Linux syscalls. So how exactly would that work?
So in practice, we don't run that on a bare metal platform. We run that on a normal Linux virtual machine. Because the thing is, we want to test that for a bare metal, you don't test an interaction with the operating system, as you said. We test that the compiler can generate correct code for that architecture. Like a bare metal system, of course, if you want to think about an embedded device where you have like sensors you need to interact with, there you need to have special tests for them, but that is not the concern of the compiler. The compiler is only concerned about generating machine code that works on that architecture. And whether you test it on
on a Graviton-free AWS virtual machine, or you test it on a Raspberry Pi, or you test it on a Raspberry Pi Pico microprocessor, it doesn't change. And so in practice, we are able to, with this way, we are able to run the tests on a standard Linux ARM virtual machine.
Thank you very much for your talk. That's very informative. On the topic of the difference between qualification and certification, I was really interested here that, once something is qualified, you can just, as long as you use the same methodology, it keeps its qualification even when you change things. Does that apply for certification, or do you need to draw a line in the sand?
Okay,
And,
so to clarify that a bit, when you still have to submit every qualified release, like every time you make a new release, you still have to submit it to the assessors for review. Like you can agree on a process with your assessors to say, if I make these specific changes only within these boundaries and I verify them myself, and they're like just, for example, bug fixes, then you can agree with the assessors to say, then we don't need to go through you. But otherwise, for any release, you have to still to go through them. But if they already reviewed that process, and if that process was already agreed upon, they don't have to review it again. Because like once they agree that something is safe, they cannot really say, no, it's not actually safe. And so keeping the set of things that change small just means there is less work for the assessors to do, and so it takes less time, it's less expensive.
Thank you for the presentation, and kind of more importantly to me, thanks for everything you've done over the years on Rust infrastructure. It's insane how it all just works. My question is, how useful is static analysis in finding tests related to requirements or finding which invariants have changed? Like, how much do you employ static analysis for this?
The effort was fully manual. So we were like, I cannot say enough how good the Rust project is at quality management. It doesn't, the Rust project doesn't call it quality management, and the Rust project cannot get qualified because it's volunteers, it's not a legal entity. But we relied a lot on the work they did. And in this specific case, the Rust test suite in the past recent years has been reorganized so that, for example, all of the tests that verify the C ABI are in a single directory. And so, for example, that work we can do is, the way we did it, we just went through all of the directories. And for some directories, we said, all of the tests in this directory are for the ABI, if it's in the ABI directory. It might not be super granular, but that was enough for the assessors to approve. And then other times we just manually read the test and decided which test section to annotate it to. And I mean, like, this is also like pick your battles. Like, you could write a perfect static analysis tool. You could just make sure that we could have written a fully new test suite that tested every single paragraph. But that was too much. Like, that wasn't required. And so, like, it's also a good challenge of safety critical. Since the standards don't say exactly what you need to do, but just a vague goal, is also figuring out what you actually need to do and what is just overhead that doesn't bring any extra safety.
What's the philosophy of the nightly features with the spec? Do you guys add them, do you guys avoid them, or something else?
That is actually fairly easy because we don't allow you to use nightly features in qualified compilers. And the specification only, like, the first language specification is not something you can just take and build a new compiler from it, just reading it, because it was built only to be our requirements document. Like, borrow checking in the FLS is described as you need to, the compiler must ensure references are valid. It doesn't describe algorithms because that is not a requirement. And so like, if there's an IT feature that is not used, that users cannot use because they are not allowed to buy the safety manual. There is a constraint of, there is not a constraint like, they're just not enabled in stable build, but like we say, you cannot use the magic environment variable to enable unstable features. And so like, it's, we don't cover them.
So how often do you intend to release a new qualified version?
We haven't yet published any specific plan. What I can say is we are planning to release more than one qualified long-term supported version a year. We are still finishing the evaluation on how much actually is feasible because we would like to release new versions as frequently as possible because we have the infrastructure, we have the automation to do it. We need to check with our sensors in practice what velocity can they sustain and what is reasonable. But surely one a year, probably more than one a year, and we'll announce it soonish. So yeah, stay tuned.
How does so the question about nightly was interesting because then the core library kind of uses unstable features internally, but then you have to compile that through the compiler as well. And so I mean, as far as I understood, as a user also currently, that's your job to make sure that the core library you use is correct. Like, how does that work if you're not supposed to use nightly?
Yeah, so the way that we are going to qualify certify the core library, we are still ironing out all the exact details, but the advantage of being the compiler vendor is we can say, this native feature can be used just by our library, and we just specify it enough so that it works for our library. Like, being the toolchain vendor, we can do that for if you are a customer that you want to certify the core library yourself, probably the best is to get in touch and we can figure out how we can enable just the smallest subset in a specific way to make sure you can do it it's going to be complex and there is no off-the-shelf solution yet for that. It's the next thing we're working on. And hopefully I'll have a talk in a few years on how did we certify the Rust core library.
This is the last question. Last question.
Yeah, thank you for the talk. Not sure if this is a silly question, but do you ever see a future where you could upstream like the spec and the processes to kind of the main compiler, and kind of every Rust compiler would be qualified to some of these?
Okay, so we do upstream a lot. So like we try to upstream as much as possible, and we are in close collaboration with the Rust upstream specification team to make sure to check how much we can share the work. Because like we did all of the work and it doesn't make sense. Apart from the fact that we are an open source, it's all open source. So if a competitor wants to base off our project, they don't need that we upstream it. They can just base off of Fersin. So like we try to upstream as much as possible on the code side. So the annotations are not yet upstream because they don't make sense without the Fersin language specification. And the specification, we are working with the upstream team to see what is going to be the good shape for the official specification. Because, as I said, our specification has very limited requirements to be our requirements document. An official specification will be more detailed and will cover more use cases. Regarding processes, we can't. Because the processes describe how we, Ferro Systems, qualify the compiler. If you create your company and you want to base off of Fersin, you will have to change the qualification plan and change the processes, because those are the processes that work with our infrastructure with our way of developing. You will need to come up with your solution. So our processes, as they are right now, they cannot be, they cannot be upstream, because upstream is not following those processes, and it doesn't make sense for upstream to follow them. They have their own, which make, and the requirements for a 20, 25 people small company are vastly different than a 300 people open source project. So, I mean, Qualifying also means taking liability and providing long-term support, so it's not something that I see the Rust project taking on. But yeah, as much as possible, we try to upstream and give back everything we can to the upstream project.
Great, please give them a massive hand. We're going to head to lunch now, so if we could all head back down into the exhibit hall for lunch, please. Thank you.
Yay.
Hello, everyone. Thank you all for coming back. Hope you've had a great lunch. Very happy to introduce one of the most biggest characters in the Rust London community. Please give a big hand to Daniel McKenna.
Okay, so let's just... Okay, so today my talk is on creating a text-to-speech system in Rust. And with this talk, we have a completely open source text-to-speech system. It's going to be great. But first off, let's just do the initial stuff. I hope everyone's having a great conference. It's been great talking and seeing so many of all of you. And big shout out to Ernest for organizing this. I don't know how he does it. Man's a hero. And for me, I'm a programmer at Emotech, an AI startup primarily using Rust for our services, not Python, Rust. I also, we work in speech technologies, related areas. We do text-to-speech, speech-to-text. We do lip sync, which is taking in text of people speaking and generating 3D facial animations. And we're also hiring, I have been told to mention that by our HR person, so obligatory advert over. I'm also XD009642 online, which is maybe a bit of a hard name to remember, but you can also find me via my big open source project, Cargo Tarpaulin, an open source code coverage tool. Now, this talk's going to introduce TTS Systems, the challenges, and it's going to cover all stages in the pipeline. So that's from characters and text coming in to audio coming out. And like I said, we have a fully open source text-to-speech engine and 2 accompanying libraries, one of them which we use in production. And with this, you'll be able to take my code and you'll be able to turn text into speech on your very own computers. So why Rust? Well, sometimes AI systems need to be real time. We care about latency. People care about this a lot in speech. There's a lot of talk about real-time factor, and we need to be handle concurrent load from users, and Python breaks pretty quickly in this scenario. I don't know if anyone here has done speech before, but if you have, Caldi is probably a familiar and terrifying name. It's a C++ library, and it is what the majority of ASR, so speech to text, the opposite end round, it's what the majority of those systems were written in. They weren't using TensorFlow and PyTorch. They were using Caldi. And researchers and C++, they're not engineers, and there are some issues. So we want our researchers to be able to help us on these systems. We want to work on them, and we want confidence in production, which is why we pick Rust. And also in text-to-speech land, there are some people still using HTK, which is a hidden Markov model toolkit. Once again, it's a C-based system, and these things are hard to use, and they do come with safety issues that can be seen in production. So what's hard about text-to-speech? Well, language is hard. We have unknown words. You'll train your system, and then you'll come and someone will create a new company called some word that you've never seen before, and you have to figure out how to say that. You have homographs, so words that sound the same, lead, lead, bass, bass, and you have code switching. This is more of an issue in foreign languages, but if you do something like Arabic text-to-speech, which we do, you will find that customers often put English words in, often proper nouns or certain words. No one's ever bothered trying to translate Kubernetes cluster to Arabic. They just say Kubernetes cluster in the middle of a sentence. So you have to deal with changing of the language and identifying that. You also have to think about how the speech sounds. In text-to-speech, we're constantly balancing between 2 things. We have naturalness. We have, if it sounds like a real person talking, how natural it sounds. But we also have intelligibility. Text-to-speech is used for accessibility systems like screen readers and for things where people need to be able to understand the speech better to communicate and interact with us all. So you do have to think about what your system is targeting. Are you targeting accessibility needs, or do you want to just really sound like a human being? And also, you want to be able to control things. People want to be able to control volume, speed. They want to be able to tweak all manner of things, add pauses into the speech. So we all need ways to do these things, and that's what makes text-to-speech challenging. So now I'm just going to go over a bit of how we've done things in the past. So we've done formant, synthesis, And what a formant is it's a resonant frequency in the vocal tract. And by taking all of those resonant frequencies in our vocal tract, we can add them together and we can make sounds. This is how the very first systems worked, and they essentially tried to create a mathematical model of your entire vocal tract from your lungs to your lips and everything that moves in the middle. And then do things like when someone makes a t sound. How do these things change? How do these signals change? So they're really hard to make, they're very fast, they sound robotic, but they are so intelligible, they're so easy to understand. You don't get like issues that you might get with neural network systems where it's learned to mimic all the stupid things that we do when speaking, which makes things harder to understand. But it's incredibly low level, so it's very hard to develop. And that's part of why these systems have fallen out of practice, because you do need to work so hard to just get fractional gains in like how good it sounds. We have concatenative synthesis, which has a very easy to understand name from it. You're just taking bits of audio and you're just gluing them together. So what we have is a database of audio samples or units. These are normally subword units because we don't want to keep every word in the English language. We usually use phonemes or groups of phonemes and we join them together. They sound incredibly natural, but at the points when you join, obviously that's a cut in a sense. So a lot of work in these systems is smoothing over these joins. And these are good, but a lot of data, and they have their own challenges. We have hidden Markov model-based synthesis. This is actually what I initially wanted to do the talk on, but it's very hard to do. It's based on a statistical model that is spatial temporal, so it is a statistical distribution over time. It was state-of-the-art pre-deep learning. There are some versions of it that utilize some deep learning for parts of a hidden Markov model, and duration modeling is tricky. So a hidden Markov model kind of assumes that every Markov state lasts the same amount of time. But when I speak, every acoustic unit that I'm speaking does not last the same amount of time. So you have to find ways to trick the statistical model into doing that. And that was one of the things that made this hard. It does work really well in languages which have a more consistent timing or different type of timing, I should say, than English. So you will still find it sometimes actually used in Japanese text-to-speech systems. There are still universities doing that. And then there's deep learning, of course, what everyone expects to hear in an AI talk. Neural networks. These tend to be in two flavors. You either have you put the text straight in and audio comes straight out, or you generate a spectrogram, and then you have a vocoder which turns the spectrogram into audio. Now, our system, we're going to be doing this spectrogram vocoder system. We're going to have text normalization, spectrogram generation, and vocoding. And these are essentially the sections of this talk. But first, what is speech? Who knows? Well, hopefully we'll all know at the end of this. So fundamentally, we can break speech down into different subunits. We can break it into letters, which the linguistics community call graphemes. We can break it into syllables, that's each individual sound in the word. So you can think of it as the beats of the word, like syllable has syllable. And I'm teaching you all how to suck eggs right now. You have phonemes, that is a language-specific sound that forms words. So this is a bit more of an understanding of the language. So can is one syllable, but it has k, a, n phonemes. And then we have phones, which are smaller. So in the English language, tap and hit, the T sounds are different. They're different phones. But linguistically, these are the same sound in English. We don't distinguish between them like linguistically. They will never change the meaning of something. It's just based on where it is in the word. You have co-articulation. When you go from one phoneme to another, the sounds will kind of bleed into each other and you will get different sounds. Now, we don't tend to use phones, at least in text-to-speech, but they're kind of the lowest level sort of feature you can get in speech. Now, with phonemes, which are what we're going to be using, spoiler, they're really useful. You can get phonetic transcriptions of things. I'm sure a lot of people have heard of IPA, the International Phonetic Alphabet. When you go on Wikipedia and it tells you how to pronounce the article name, it's given in an IPA string. Now, IPA is super common, but we're going to be using ARPABET. Alphabet is an American English phoneme model, which was popularized in the speech community with CMU Dict and initial speech research. CMU Dict is open source, and it's a phonetic dictionary of common English words at the time. Now, the advantage of phonemes is we're unambiguous. We turn the text into smaller units. We don't have to think about, is this a silent letter? You know, what sounds are we making? We've described what sounds we're making explicitly. Now, sometimes end-to-end deep learning systems won't use these. Personally, I think that's, as the youth would say, an L take. Like, that's pretty bad. You can't control pronunciation. You will hit words that your system has never seen, and you will pronounce them wrong. So you need to be able to give users the ability to tune that pronunciation. Well, is that it? Well, no, there's more to speech than the sounds you make. There's also prosody. So this kind of comes for rhythm, intonation, pitch, and this differs language to language. So Mandarin is a tonal language. The tone of the words changes the complete meaning of it. Now, English, we do use tone actually to symbolize things, but we use it more as a grammatical construct. We use a rising inflection as a question. This is a way that we use pitch in English to signify the meaning of the sentence. We also have the timing of words. So English is stress-timed. There is an equal amount of time between stresses in your speech. And part of English intelligibility is putting the stresses in the right place. If people put stresses in the wrong place, or they don't time the stresses properly, it makes it harder as an English speaker to listen and understand what they're saying. This is kind of what we talk about in language learning when it comes to fluency. Mandarin is syllable-timed. Some of the Romance languages are syllable-timed. There's Mora-timed, which is pretty much just a Japanese thing. If anyone wants to know, I can tell them at the end what that is, but we're not going to dive too much into other languages. And now we can actually start doing our TTS system. So, text normalization. We want to convert the text from the written form to the spoken form. Written text is ambiguous. So we need to normalize it. We need to actually move it how we want the TTS to say it before we do anything else. Now, traditional systems were rule-based. Linguists tried to make like big decision trees telling you how to change things. There are models for it. GRUT, or GRUT, however you say it, G-R-U-U-T, is a popular model, which is a mixture of rule-based and hybrid, I believe. Now, hybrid systems are good because they let you do a bit of customization. They let users be able to add their own rules or something. And I kind of went for a simple rule-based approach because I don't want to be training too many models. I did have a limited amount of time to do this talk. And I do have to shout out Unicode segmentation and the de-Unicode crates. We do have to handle Unicode, and these crates are necessary tools in your toolbox doing this type of processing in Rust. So, for the challenges, we have to identify some level what each token is. We need to tell how to read numbers, like that number, is it a year? Is it 1971? Is it 1917? Is it 1971? Like, is it a PIN number? It's not a PIN number. Well, it's someone's PIN number, it's not mine. As a sequence of capital letters and initialization, or shouting, or a word. The Saudi smart city, NEOM, they write it in all capitals, but they don't want you to go N-E-O-M, they want you to go NEOM. Now, this gets a bit complicated. Can we just get users to do it? Like, I don't want to do work, I just want users to do things, right? Well, luckily, there's a W3C standard for this, SSML. It's an XML standard, speech synthesis markup language, and you can use XML tags to give instructions to a text-to-speech engine. Also, as someone who's worked on a system that didn't have it, and then we had to bring it in, you should be bringing this in from day one because it will drive your normalization, it will make it easier, and if you try and bring it in retrospectively, you're going to have to do a lot of refactoring, and like you're going to kind of hate yourself for not like thinking more about things earlier on. So here I have some example SSML. I have one pecan. We can show that it adds a break. It's told you how to interpret the number, and it's given a phonetic transcription. You can do other things like speed, volume. You can specify which language if you're changing the language during audio. There's even some stuff to like add in audio files and play them because they're initially thinking about using this in websites for like accessibility things or like as subtitling solutions. So we have SSML. So we're going to do SSML parsing and normalizing. And this is the first bit of Rust code. I'm not going to show you all the code, but I work with researchers, and one of the things which I didn't expect when going into things, so we've all seen Rust enums, we can attach data to them, that's brilliant. Our researchers are new to Rust, they're coming from Python or C++, and they're not used to pattern matching or languages with pattern matching. So we found one pattern they were trying to do a lot, was doing like cloning the enum to like try and extract and compare the value because they couldn't just compare with equality. So we tend to do a simpler enum without the data attached, and we give them a method which then lets them do equality to compare. This is a bit easier than like having them add so many unnecessary clones or doing weird things with if-let to try and like compare enums because they don't know pattern matching yet. And it's sort of, it gives them an easy mode to do Rust. And that's important. Like, it'd be great if they could just stay in their research land and chuck things over the fence and we can do it, but that's not a great way to do a project. We want to be collaborative. So that's just a little aside on the code. But even if we do SSML, we still have to normalize. So the approach I've gone in the code, which you can all check out afterwards, is I turn the output into a list of chunks. These are either text, phonemes, or state changes for the TTS, like applications of like pitch changes, breaks, pauses. For the text, we split it into words, grab the punctuation, normalize each word. I don't keep any major context. There's a bit of context around numbers, just to try and get them roughly right, but I don't handle things like BAS and base and trying to figure out which one's the right one. Rule-based systems for that don't work. They're really bad. Like, you should just train a model to do it. In future, I might do like an open source model just to demonstrate better, but there's stuff in Python that anyone can look up if they want. And we've done all this, and we have our dictionary, and that's all great. Dun, dun, dun. No. So we've taken our dictionary, we've got things to phonemes, but in the system, like I said, there'll be unseen words. So there's not one in my TTS system yet, maybe in future, we'll see. But we would use G2P systems, grapheme to phoneme. So these models would traditionally assume that each letter goes to like one phoneme, and they're trying to add like padding null phonemes to make things line up one-to-one. But these approaches don't work very well, and you can kind of see here with the word accuse, like I have the phonemes at the bottom, I have the letters at the top. 2 letters map to one phoneme, 1 letter maps to 2 phonemes, 1 letter maps to nothing. You do need to use like more modern sequence-to-sequence models or things like CRFs or HMMs to do things. You need to be able to do things that can handle with unaligned sequences and statistically learning the alignment if you want the best results. So we've got our phonemes, and now we're going to generate a spectrogram. So why do we generate a spectrogram? Why don't we just generate audio? Like, we want to listen to audio. We don't want to like look at pictures of audio. Come on, guys. So the more you constrain a problem, the easier it is to train a neural network, and the less data you need. A spectrogram is an incredibly compressed representation of audio. We've quantized it on the time scale to like whatever our time window is, say like 60 hertz or whatever, like 0.01 seconds a frame. And we've quantized it based on frequencies. And because of that, we can massively reduce the amount of data, give the neural network an easier structure to learn, and then require less data for training. Generally, with these type of models, you can avoid like the big OpenAI approach of like just throwing the entire internet at it if you're smart about the representation of your data and just trying to like really push things in the right direction. Now, this is like part of the skills of like working in data science and machine learning engineering. It's figuring out the way to guide the model to the right solution, either through architecture or data engineering. Now, we're going to use a specific type of spectrogram called a MEL spectrogram. So the MEL scale is a pitch scale that's designed on human perception, so every tone sounds equidistant. So it loses resolution outside the ranges of human hearing, and it has the most sort of data where our hearing is strongest, which is in the range of a human voice because we are designed to listen to each other. And this sort of ends up for frequencies then binning them further into different buckets. So we've compressed the data even more. And we've kept it to the stuff that we're interested in, like where human speech exists. If we've recorded our data with the same microphone, we will have the same high-frequency noise or crackle, and we don't want the neural network wasting time learning the noise profile of our microphones. We want to focus on the important bits of the data. So this is, again, once more, how we constrain the feature space down more to train more useful models with less data. And the model we're going to be doing is Tachytron 2. So this is a sequence-to-sequence model published in 2018. What sequence-to-sequence means is it takes a sequence of inputs and generates a sequence of outputs. It's no longer state-of-the-art, but it can run on CPU and my old laptop, and like that generally makes it accessible. I don't want to force anyone to buy like an NVIDIA GPU to try and run the demo. That would be unethical of me. And we're going to do something more interesting with our neural networks, and in this project I avoided using PyTorch or TensorFlow because, well, everyone uses that, it's a bit boring, and it lets us look more at the Rust ecosystem and what people are doing in the machine learning space, and also things that could potentially run on more devices, including edge compute or embedded devices, because there are runtimes like Tract which are suitable for that. And because of that, we exported the neural network to Onyx. This is an open neural network exchange. It's an open standard designed to make it easier to run neural networks and share them between like different frameworks. But as a relative outsider, the adoption feels poor and the ecosystem feels lacking. When it works, it's great, but there's limited support even in Torch and TensorFlow. Like, they're not great at everything. Torch can actually generate invalid Onyx in some cases, which sucks in its own way, but you just kind of get around this stuff when you work with machine learning code. It's all held together with like bits of string and elastic bands, like ultimately. Now, the best native Rust support is in Tract, which I mentioned, but the general best support in the ecosystem is the Onyx runtime, which is done by Microsoft, and ORT are the bindings to that, and it's pretty much fully featured. If you work with Onyx, I've got a list of useful tools. There's Netron that allows you to visualize the graph. You want to be able to look at the nodes, how things connect, what the dimensionality is of your inputs, what your input names are, what your output names are. There's an Onyx optimizer crate, which I think is actually like, they're no longer working on it, but it can optimize your graphs if your Onyx library doesn't have a graph optimizer. And NVIDIA have released a lot of Onyx tools. So Graph Surgeon lets you basically hack around with Onyx graphs with Python, remove nodes, change nodes, do all this sort of neural network introspection and messing around, which can help you get past some compatibility issues in the ecosystem. So going back to compatibility issues, a recurrent theme with neural networks, it seems. The Tachytron 2 Onyx export splits the network into 3 subnetworks. And this is because there are general nodes which most things don't support, and they don't support well. They also have an Onyx exporter for the vocoder that comes with Tachytron 2, but it actually crashes whenever I try and run it in their Docker image. So something's gone wrong there. I'm not quite sure what, but we're not using their vocoder anyway, spoilers. So it doesn't matter. Now, in the pure Rust corner, we've got Tract. So this is the best Onyx support in the ML ecosystem. It's missing loop blocks, which they are planning on adding them at some point. PR's welcome. So that's fine. They're missing dynamically sized inputs, but that doesn't matter too much. When you export a model from Torch, you do something called JIT tracing, and that fixes all the input sizes. It can potentially perform some optimizations, like Tract in its main branch has optimizations, but I don't know if they do any optimizations in Tract Onyx or how far they are. And it has a real-time factor of 300 on Hello World from Rust, my default test string. Real-time factor of 300 means if the audio is 1 second, it will take 300 seconds to generate. So that's not real-time, but Tract was designed for like the Sonos smart speaker and doing like wake word detection, which is a much smaller neural network and much simpler design. So this is probably just picking slightly the wrong tool for a wrong job, a little bit. And I have some example Tract code here, which is how we load the encoder and how we actually just run things. So a lot of generics in the model type, which I aliased. Yeah, I'm not too sure how I feel about all these generics. That's quite a long type name. I have my opinions. But you load the model, you turn it into a runnable, which makes it into an Onyx graph, and then to do the actual inference, they have a t-value type and a tensor type, and you wrap things in there, and then a t-vec for a vector of tensors, and you give your tensors in order, and then you've done an inference, and it all works, and you have some like values coming out of the neural network which you can use. We then have ORT, which is bindings to C++ code. So here we have the edge of danger and wildness to which we live with of native code in our Rust stack. It's got decent performance, and it can also perform optimizations. The real-time factor on Hello World from Rust with all the optimizations turned off because I thought Onyx wasn't doing, thought Tract wasn't doing any, so I turned it off to compare apples to apples a bit. The real-time factor was 2.7. When I turned on all the optimizations, it went down to more like 0.7. So big speed-ups if you turn on the optimizations. Really cool crate. This slide's actually changed a lot. When I started doing this talk, they were on version 1.0. You had to pass in the memory allocator you were using explicitly, whether you were using the C++ allocator, the Rust allocator, a GPU allocator. And I had a lot of complaints about it, but they've done version 2.0, and the API is so much nicer. Like, there's no mention of which allocator you're using. There's no passing pointers to allocators into things or whatever you're doing, but here is the code, and it's not as verbose as the Tract code, and there's no like weird generics or anything that can scare people or give you pages and pages of error messages. I do think I do slightly prefer this as an API personally, and also, as well as letting you put your inputs in as a list of inputs, it lets you do them as named inputs, so tying to the names in the neural network to the value. I'll show you why that's important later, but that's a great bit of API. So my general thoughts are ORT API is lower, you're linking to C++ code, and you have to sometimes think about building that code and how you're going to build it in your system. That's painful in its own way sometimes. If it works, and it's great. But sometimes like you end up faffing a bit with C++ build systems potentially, and like if that's not your forte, you probably won't enjoy it too much. If it is your forte, you still won't enjoy it. Actually, it's I can't pretend I enjoy messing with CMake or anything like that. Being able to specify inputs by name is really nice. They both use ND array, but Tract has a lot more wrapping into their tensor and t-value types. I'm sure there's a technical justification for that. I haven't gone too deeply into it. But the wrapper types with Tract felt like a bit more friction in the API for just getting my data into the network. But I think Tract is still a good API. Like, I'm not trying to sound bad. Like, it is good, it works, it does what it wants to do well. Like, you'll be good choosing either of them if they meet your performance concerns. So this is why named tensor inputs and outputs are useful. So as I mentioned before, the Tachytron 2 network is split into 3 separate networks. Now there's a recurrent one that runs in a loop. This is why they split it into 3 networks, so that you can do this loop manually yourself. And this is all the state that the network keeps in the iterations, and you now have to pass that in manually. Now, if you're doing this without named inputs, you're looking at the graph in like Netron, and you're making sure that your variable names match the ordering in the UI and like in the graph. And it adds an extra weight to verifying that things are correct, especially since a bunch of these are the same dimension, so you won't get dimension mismatch warnings. Attention weights and attention weights come. They're the same size. If you mix them up and get them backwards, your network's going to generate gibberish, and you're going to wonder where it's gone wrong, potentially. So named inputs are super important. If you're working with networks of any amount of complexity, you do really need these, or you need like very good tests. So this is something I wish Tract would have on the inference, but that's life. So we have 3 networks now. We need to manually run the decoder iterator, and the dynamic input dimension is fixed because of JIT tracing. So the outputs of Python and Rust don't look the same, like the code has diverged a bit too much. If we all kept it in one network and just kept it in and kept it out, it would probably be the same, but things have changed. So they don't look the same, but they look close. So this is the spectrogram generated by Python, and this is the spectrogram generated by Rust. So as a brief explanation of what this is, the x-axis is time, and the y-axis is frequency. Higher is a higher frequency. So we can also see the strength of different frequencies in the speech and how they change over time. And then if we just go to my listening thing, so this is what the Python sounds like.
Hello world from Rust.
And this is what the Rust sounds like.
Hello world from Rust.
So it's still saying what it's meant to say, and for the purpose of this talk, that's fine with me. So moving onwards, do not trust researcher documentation. Tachytron 2's text processing says it can take uppercase and lowercase characters or alphabet phonemes. So I went into this expecting to use my phoneme code, which I spent so long working on, but the pre-trained models weren't trained with any phonemes, and they also weren't trained with capital letters. So that data going into the network does not know what to do with it. And as such, when I put in my phonemes to say hello world from Rust, and see if you can hear hello world from Rust in this at all, because I got
Gay, gay.
and I thought I did something really wrong. Yeah, the wrong thing I did was that I didn't train the network myself, and they don't actually note down very explicitly how they train this and what augmentations they do. You have to dig into the training code a bit yourself. Also, CMU dict is in capitals, so my text normalization was output in capital letters. They seemingly trained it on only lowercase, because when I put in capital letters, hello world from Rust, I got yeah, it can take a bit of debugging and a bit comparing between the Python and the Rust. It's a lot of backwards and forwards. It's definitely a process. But we have our spectrogram, and now we can finally start trying to turn this picture of a sound into an actual sound. And this is where we have the vocoder. So in the frequency domain, the spectrograms, we have what we call the magnitude and the phase information. So the magnitude is, for each frequency, how strong is it in the signal? How big is it? The phase is more like, if you're a sine wave or a cosine wave, it's a bit of offset. So the magnitude's quite easy to understand conceptually, and you can look at it and you can kind of see what's happening. The phase suffers a lot from wraparound, and you can't quite see the sounds from that. Yeah, it's much harder to train. I don't think anyone actually trains things to output phase spectra. So part of the vocoding is actually estimating the phase so that we can generate audio from it. So in the Tachytron 2 repo, we have the parameters for the MEL spectrograms that they generate from the training data and that the network will then generate. We can then use them, and we can use them into a vocoder and generate sound. As an example, I have the linear spectrum, not a MEL spectrogram. I have the magnitude and the phase. We can see from the magnitude, we can see the shape of how the frequencies change in time, it gets a bit higher and then it drops off. From the phase, I can't tell when a word begins or ends. I think if you can, you should possibly submit yourself to study by scientists. So yeah, this just illustrates why we use the magnitude spectrum. So there are kind of two approaches, or there's a few different approaches. One approach is to use a neural network, which you train on the magnitude spectrum and the speech that generated that spectrum, and then it kind of learns the characteristics of a human voice, and it gets a bit better at making it sound like a human voice. Or you have signal processing, which is way, way too mathematical for me to show everything and how it all works. But what we do is for general steps, so I should have mentioned we do Griffin-Lim in this thing. It's a fairly well-understood algorithm, well-understood performance characteristics, but we convert from a MEL spectrogram to a linear spectrogram. So like I mentioned before, the MEL spectrogram is essentially compression, and we're sticking things into buckets, so it's lossy compression. So we have to go back to the spectrogram with more frequency information, not just based on our perception of sound. And for that, we have to do some like non-linear optimization. I really wanted to use argmin for this, but it uses like a very specific variant of some optimizer, which has only been implemented in C, but there's a crate with bindings to it. It's like LGBFSLB or something. It's in the code. I saw someone mouthing it, so yeah, I can check later. But we create the spectrogram. We then create a random phase spectrum. We create a completely random matrix. And then we do a inverse Fourier transform to turn that back into audio. And then we turn it back into a spectrogram. This is an iterative process, so kind of what happens is we know our magnitude spectrum's correct because the neural networks are infallible, of course. But when we do the inverse transform back to audio, some of the information bleeds out, kind of goes from the magnitude and into the phase when we turn it back, and our magnitude and our phase spectrum will be different from when we started. So then we restore our original magnitude spectrum and keep the modified phase spectrum, and then we keep changing it and doing that again and again. And eventually we'll get something that when we do the inverse transform, the magnitude spectrum isn't changing. It's sort of converged on some point. And there's probably some like great mathematical proofs on why this works. Like I kind of have an intuition for the maths. Like I said, like the information kind of shifts between the two and you go to some form of convergence. And we can listen to this, of course, and hear how things work. But for this sort of signal processing, nonlinear optimization code with a bunch of big matrices and all this complicated stuff, like how do we test it? So we go from a reference golden implementation. Like I said, this is a well-understood signal processing algorithm. Like there are implementations of it. And what you do is you take one of those which is appropriately licensed. You break down each part of the pipeline, and you can generate the inputs, get the outputs, compare them. Comparing matrices of floats is painful. Like you can bring in ND array of procs and then do a assert a procs equal on like a 300 by 80 matrix, and your developers will hate you like when they're trying to bug fix on that. So I think on this crate I ended up looping through all the values and reporting the first one where it went wrong, but the important thing that when you actually have the test fail, you want to detect it, save a bunch of matrices to your file system, and then you can compare them to the matrices in some sort of plotting script or something that just makes it easier to introspect about the data and what it's doing. Naturally, test with realistic inputs. I have met people who have done things like generated a random like matrix and put it through, not actually a magnitude spectrum, and they've got random noise coming out. It doesn't actually hit like branches or aspects of the code that you want to test, so you do want to like make sure your data is representative of your system, which is like an age-old adage. Your test data should kind of match what you're expecting to get, what you could feasibly get. And as you iteratively build up the pipeline, use unit testing to test your understanding of the system and the maths. You don't want to be implementing these algorithms, ideally, and then kind of go at the end of it and not understand how any of it works. If it doesn't work, you need to be able to fix it, and to do that, you need to understand it. So porting can be a great learning opportunity to learn a bunch of maths you haven't done since university, and a chance to get back in with all the Fourier transforms and stuff. Who doesn't love that? So, as a note from the implementation, we ported from Librosa. That is a Python audio processing library. It has tons and tons of features. It's very fully featured. It's never seen production. We implemented this so we would have something which has a known real-time factor, and we could compare against some newer neural vocoders we were experimenting with and like changes in our architecture. We kind of wanted to be like, well, is this competitive with like the simple fast approach? Is it not? How does it compare on GPU versus CPU, etc.? This crate has never seen production, and I've not published it onto Crates.io, but it is open source. It does have some unwraps in it. If you want to use it, you're free to, and while it is tested, it is less tested. So how does it sound? Well, Griffin Lim doesn't have a model on how human speech sounds. It just tries to do something simple and quick. As a result, there are aliasing artifacts and the like in the audio. It kind of sounds a bit watery, but if I just play this, so it won't sound as nice as the first samples. They use the neural vocoder, very state-of-the-art stuff. This is what the Griffin Lim one sounds like.
Thank you for listening to my talk.
So you can hear the speech, but it's got that kind of watery, warbly feeling. Just all Griffin Lim audio sounds like this, but at least it's understandable as human speech. So now we have the links. So on my own repo, I've called it XDTTS because I'm bad at naming things. Sorry. On the Emotech Lab one, we have the SSML parser. So there's a lot of credits for writing SSML because that is a way you talk with third-party TTS APIs. There's actually no credits for parsing it, and there's very few libraries for parsing it in the open source world because no one likes writing libraries to parse XML standards, and you're only interested in it if you're making a TTS system. So we've open sourced this, and we've also open sourced the Griffin Lim stuff plus tutorial. So I do have bonus content. How good am I for time, Ernest? I'm great. I got through this a lot faster than I thought I would. So if I didn't expect to show my wallpaper. Love Godzilla. So yeah, in the Griffin Lim, I am on the Wi-Fi. Yeah, so we have bonus content. Who doesn't love bonus content? So I really wanted to talk about signal processing, but I knew the maths would lose a lot of people, and I remember the lectures in uni being painful, looking at someone going, if you take the sum of sine waves and cosine waves, you can make any periodic repeating signal. We didn't come here for this, we came here for Rust. So I do have a tutorial that actually goes through a bit of the signal processing if you want to go more into that. And bonus content. We do naturally have the TTS code. All the slides are in here. There's content I had to cut, so I initially tried to do a network called Speedy Speech, and because of Onyx support, I had a lot of trouble with that, but of inference code for different frameworks. There are some frameworks missing. A lot of the pure Rust ML frameworks are very nascent, and some of them don't work, or they have issues for some of the stuff I was trying to do, and I didn't want to put anyone on blast oh, your crate doesn't work, mate, what you doing, bruv? So if I haven't mentioned anyone, it's either because I haven't heard of them or things didn't quite work when I tried them, but I might have tried it a long time ago, so things could change, look up in the world, what's happening. And for the modules, I have doc comments on how everything works. For the text normalizer, I've got a big write-up on text normalization, and I also cover things with different languages, like how to handle different writing systems. Some of the challenges that come about with Japanese or Arabic or Mandarin and all this stuff. And in the Tachytron 2 module, I have doc comments explaining sequence-to-sequence models and linking to papers and references and anything that you might want to look at in order to further understand more about these architectures. I was initially going to look at doing some training stuff, so the training folder's largely data set analytics stuff. There's no training code, but you can look at a data set like LJ Speech and see what the collection of diphones are, what the collection of phones are, what the word, how many out of vocabulary words there are compared to CMU dictionary. All these sorts of things that you do when doing data exploration and training, just to try and understand what you're working with and how you could potentially do things. And yeah, that's generally it. Obviously we're going to have questions after this, but for the future, things I plan on doing, there is a right down bottom here at the corner, there's a file called TDP Solar. That is how to change the speed or pitch of audio so you can use it to change the speed of audio without changing the pitch, or change the pitch of audio without changing the speed. I am working on an implementation of that, so I can build in all the SSML support for changing the speeds and stuff. I do want to do a G2P model just to show that to the open source community, and I would probably like to try and throw in maybe a few more MelGen models just to integrate more stuff. I do plan on writing more about this and putting more stuff out, things which aren't suitable for a conference talk, but are suitable for digesting in your own time. So yeah, hopefully this is educational for people. You can also dive into all the Rust code. I didn't show too much of it because I figure this is a very new domain for a lot of people, so you might want to just learn the problems that we're dealing with and a bit how we deal with them. But yeah, any questions?
First of all, give Dan a massive hand. Yeah, we're ready to take some questions.
Oh yeah, there's a question over there.
Hi, thank you very much. I wonder where accents fit into all of this, because at some point you need to be opinionated about how you pronounce R's, or Bath versus Bath, etc.
Yes, it's always Bath. I'm just saying that now,
Agreed.
Good. Yes, so this is actually a very interesting thing and very relevant for what we do at Emotech. So we do a lot of Arabic TTS, and Arabic is a non-standardized language. No one speaks modern standard Arabic. They speak local dialects. You generally kind of pick what accent you want, and you get enough data on that accent, and you train the model on that. Normally when you train a TTS model, you're training it on a single speaker. There are high massive data approaches which use tons of speakers, but yeah, you normally try and pick one speaker with one accent. We've done things like Arabic accented English, where we had an Arabic speaker to record a few hours of Arabic audio and a few hours of English audio, and then the TTS can switch between English and Arabic, keeping a consistent accent. It's very much a data concern. Any other questions? You can also ask me to get the TTS to say something. I will.
Nothing rude, all right? Nothing rude.
Nothing rude or controversial. I will veto some things.
I'm sorry, I don't know if you covered it, but you mentioned that certain languages are tonal. So, and you said that you've got your that your extensions, which is Solar's, to do with speed and pitch. But is that not going to be harder with the tonal languages, where you'll have to change the pitch almost twice in certain syllables?
Yes, so with tonal languages, once again, this is a question where the answer is chuck it into the neural network. Tonal languages generally have a way of writing them in Latin script, which shows the tonal indicators. So Chinese has pinyin, which has the numbers for the tone modifiers, and what happens is when you put it into the neural network, you have the pitch and tone information with the phoneme information, and it's learning a combined representation. So you're not changing the pitch manually yourself, you're trying to rely on the network to learn the pitch changes. This can be challenging on some languages. For example, Japanese has something called pitch accent. That's what linguistics call it. The Japanese call it intonation. But generally you have rising or falling pitches on certain words. You don't need, different accents have different pitch accents, but TTS systems of Japanese often get the intonation wrong because they haven't either got enough data to learn it, or it's kind of, it might be context-based. For Mandarin and stuff like that, where it's a lot more rigid in a sense, it's easier for the network to learn. And got a question.
Hi, yeah, thanks for the presentation. Well, my question was going to be, why didn't you get the speech generator to give some of your presentation? But the live demo I would like to ask is, could you please feed the first sentence of that doc string into your TTS, please? Thank you.
Of course. So, let me... Where's my mouse? There it is. Okay, and I'll pop the, so let's do this. Yeah, I didn't actually end up playing that audio for the sound check. Right, so we're gonna run the network, generating the audio, and real-time factor 0.5, excellent. FF play.
Microtron 2 is encoder-decoder sequence to sequence and run mobile, which predicts a sequence of my.
Was that right? Hopefully that was right. Yeah. Yeah, it's, like I said, my text processing is rule-based and fairly simple. I don't think it liked Tachytron 2 quite there, and not sure how it dealt with RNN. Yeah, David's got, okay, yeah, sorry.
Sorry. Thank you, that was a really interesting talk. I was just wondering, in terms of doing more of the ML tasks in Rust, so specifically training the neural networks and or doing the sort of data preparation in order to train the neural networks, where are we at the moment with doing either of those two things, and how do they compare to, say, PyTorch?
Yep. So data preparation is, I think we're there, and it depends on what your data is. Hugging Face have Hugging Face tokenizers, which is great at preparing NLP data. Previously, I've done data preparation stuff for processing video data, where I've ran OpenCV and FFmpeg, and like I've dumped out a load of frames. That's stuff which you don't want to do in Python because it takes days to run, but in C++ it took like minutes. We do some of that data processing in Rust now when we need to do it. It's quite fast and quite good at doing it. I think we're perfectly there. For training, we have actually done some neural network training in Rust. We've offered services where we've let clients fine-tune a locally hosted model on their own data, but we don't want to show them the model because that's our secret sauce, right? So we use the TensorFlow bindings and we add things into the graph and we do it. It's very much like the training API you get with Python. You're kind of just writing how that calls the TensorFlow API underneath, so it's a bit ugly, but it's possible. Generally, I would say for research activities, just keep it in Python. Like, you don't want your training in production, usually.
Cool, well, fascinating talk. Really enjoyed it, thanks. For text-to-speech, is it a thing to use like a language model and LLM to generate to figure out add more context, just from a piece of string like that, add the context and add more, and then add like emotion to it, to the text, so to make things up, almost to hallucinate what it would be more natural to be.
So I've not seen anyone using LLM for emotional stuff, so we've done a bit on trying to get emotional inflection a bit into TTS. It's generally getting people to read things with a certain emotion and then just training the model and trying to tag it like that. LLMs do slightly have a use, like I mentioned, for model-based approaches for text normalization. You could essentially do a fine-tuned small LLM to do that kind of tokens come in, normalized text come out. That's very much like the neural network architecture you'd use, but you'd want it to be a small one if you want to like do it in real time.
One more question, last question.
Do we have? No, it's
Sure, going once.
Going once, going twice.
All right, give Dan a big hand, please. We're going to have a room change now, and then we're going to have Chris Biscardi's talk. Smashed it. Hello, everyone. Thank you all for being here. We are really excited to have our next speaker. You all know him from YouTube and all the amazing videos he does on there. Please welcome Chris Biscardi. Give him a massive hand.
Appreciate it. Hey, y'all. Thanks for coming. Thanks for hanging out at the end of the day, end of the conference. This is who I am. Some of you know me. I've met a bunch of you already, so thanks for coming up if you did. Specifically, thisweekinbevy.com, if you're here for Bevy. Weekly Bevy, and so, this talk is going to be about the ergonomics that Bevy offers from a REST API's perspective. So how many people have used Bevy at all? Okay. How many people have shipped a game? Okay. So this isn't quite an intro to Bevy talk. It's Bevy from like a REST API's perspective. So for anybody on the internet that hasn't used Bevy, we might get a little bit more into the API details than an intro course. But this is roughly what we're going to talk about. We're going to talk about a little bit more. There's a whole lot to talk about. If you're unfamiliar with Bevy or wondering what people are actually doing with Bevy, TinyGlade is one game built with Bevy, heavy on procedural generation. They've been around since, I think, 0.6. We're on 0.13 now. They do their own custom renderer. They use Bevy ECS and stuff. It's wonderful. There's some non-game usage of Bevy out there. Foresight Spatial Labs does a whole bunch of physics simulation, rendering, things like that. Scientific research visualization in Bevy, which is very cool. And then, more games. This is a fantasy colony sim builder. Bevy is a very, very large project. I do a lot of educational work with Rust, kind of talk about people writing their, first 10, first 100, first 1,000 lines and how to pick a project somewhere in there. Bevy is 130,000 plus lines of Rust. So it's a lot. It's a big project. There's a lot of APIs. There's a lot of tests. Which brings me to the main takeaway from the talk is Bevy deals with a whole stack of APIs. They all compose together in different ways. And to me, Bevy is basically the progressive disclosure of the complexity of building these kinds of applications and games. So we're going to start at the beginning. It's the end of day 2, so y'all have all seen this already. We're going to talk about preludes to start. So this is basically Bevy Hello World, but it doesn't really run anything, right? So we've got use, Bevy, prelude, star at the top. It basically does nothing. It runs and it stops. We've got app new, run, whatever. But preludes, right? A lot of crates use them. Some crates don't. They're mostly good if you're doing API design. If people are going to use your crate, they're going to use some set of it. If it's not the total set, it's going to be an 80% set or whatever. Preludes are great for that. There's very little downside. The only downsides are kind of which crate does this item come from? If you're a new person and you don't have Rust Analyzer set up yet, you have no additional tooling, you're looking at a file, there's 5 preludes that all got imported. But I mean, that's, a little bit more of an edge case, preludes are generally very good things. They're used by a whole bunch of projects. Here's a couple: Bevy, Wasm, Bangen, Rand. If you've never looked at standard, standard is a prelude. That's why you can access things in your Rust files without importing them. Sometimes they're not needed. Iter-tools, all of the functions that you're going to use on iter-tools, it's an extension trait. It extends iterator. Therefore, all of the functions are on that trait. You only need to import one thing. You don't really need a prelude. Also, if you export everything from your crate, you probably don't need a prelude because it's everything, right? It's going to be everything from lib. So, constructing app is kind of our next thing to talk about. And how do you build those functions? In this example, we see app, and app comes in from the prelude we just talked about. So we've got new, and we've got something that kind of looks like a builder pattern, kind of looks like the beginning of a builder pattern, not quite a builder pattern yet. So let's talk about app and why we're using this new function, right? So app is difficult to construct manually, is the way that I'll phrase it. It's almost impossible to construct manually because there's private fields. But even if you look at world, you look at box, dine, fn once, you look at this interned dine schedule label thing. Like if you're a new person, you're starting a new Bevy app, or you're just like writing a new Bevy project, not something that you really want to like manually construct out and build up, right? So pretty obvious pretty quickly that we want a better way to do that. So new is the way that we do that with Bevy. And whenever, you know, constructing that app is hard, constructing that struct is hard, constructing that thing is hard, or you have kind of like limited ways to do that, app new is great. Now, app new with no arguments is basically a default implementation. So if you're unfamiliar with Rust, there's a default trait, you implement the default trait, you do app : default, you get what is basically new. But there can be other ways, right? Here's empty. Empty is the same as new, it just does less for you. So while new is what you're going to use, empty is something you might use in test, or if you have very specific use cases, something like that. We talked about how new is basically default. In this case, new is literally default. This is code snapshotted from Bevy's code. This is new inside of Bevy's code base. So that means empty is the odd one out, right? Kind of. The default implementation calls empty. So there's this like beginnings of a stack of APIs where most people are going to use new, right? Most people aren't even going to think about this. They're never going to see empty. They're not going to care. But we have new, we have the default implementation, we have empty, we have configured feature flags inside of here for turning things on and off based on what you're actually using. We're going to talk about feature flags later. But this is Bevy basically being built with Bevy's exposed APIs. Empty, of course, calls even more default implementations. So we've got a new world, we've got the absolute minimum for that world, we've got a bunch of defaults for all those private fields and things like that. The one thing I want to point out here is that the default runner is run once, right? You think of a Bevy game as something that like spawns a window and you start playing and it runs and updates and you get a bunch of frames, maybe hundreds if you're, you know, running a 4090 or something. But the default is to run once. You have to have like the Winit plugin or something to run many times or do it manually. New and things like new, like empty, are very common across a whole number of crates. This is Glam. Glam powers Bevies like Vec2, Vec3, any of the math, really. So you can see how new can take arguments. It doesn't need to be a default. If you have specific ways to construct your values, like splat here, for example, right? Same value, all 3 slots, same exact thing. Making construction easier, only requiring users to supply what they need to care about. So takeaways. New functions or methods, technically. We're going to be casual here. They're all functions. For difficult constructions, things that have private fields, things that you can't construct, things that are hard to construct, things you don't want to construct. And there are many ways to construct. You can have a bunch of these different functions. You can have new, empty, splat, you know, space shuttle, whatever. I don't know. Sometimes they're more social than technical, right? Sometimes this is a social decision to provide a new function. Yes, default exists, but everybody, when they're writing their first Bevy app, uses new. Why? Well, people are used to new. Every other language uses new for constructing new classes, new everything. So if there's a new function, people from other languages are very familiar with that. You can see here Vec2 new in Glam and Vec2 the struct construction are like a parenthesis away from each other. So sometimes more social than actually needed. Zero argument new is default. That is, if you have a zero argument new, that is basically what that's going to be. And you can prevent struct construction if you want to, even if you don't have like private fields or anything like that. So non-exhaustive macro, that kind of thing, if you want to do that. So we've got an app. It's got a bunch of private fields. How do we app? How do we get an app? How do we get a thing that works? Back to our original example, I've added a system now. So we've got app, we're doing some configuration, we're adding a system. We're gonna talk about that little update in a second here. Don't worry about it too much. But remember, what I said before, the runner runs once. So it'll run this app, update will run once. That's why we get one update print log out instead of like 500 or something like that. And just to point it out, default does work, right? We talked about default, new and default. New is implemented as default. You can just call default. It's just that socially, we don't do this, which is fine. So builder pattern, right? If you're using Rust, you've probably seen builders. Bevy's app is kind of always valid, right? So we don't need a special app builder because new and empty are just gonna return you something that you can just call run on. When it comes to builders, we've got kind of like initialization, configuration, and then finalization or execution. Sometimes those are the same, sometimes they're different. This is a larger example of an app. We haven't covered a lot of these concepts yet. We'll cover resources, we'll cover things like that later. But basically, app new, do a bunch of configuration, finish it, run it, your app runs. So initialization, again, we don't have an app builder. App is basically always valid for Bevy. So new and empty, they return app. They don't have to return anything else. We get a whole bunch of configuration functions on app to add things like systems, to add things like events, to add state or resources or anything like that. The key takeaway here is that these functions take and return exclusive references. So when we call one of these functions, we're mutating that original app. We don't get a new one. When we return here, we're returning an exclusive reference app that we can then drop later. So that lets us set it up in any way we really want to, but we're always mutating the original. And then we've got the finalizer, right? So in this case, we're running run. This calls the runner inside of the app. The one thing that I'll mention here is that if you tie winit to Bevy using the winit plugin that is built into Bevy, then you get a runner that runs a whole bunch of times, right? It ties it to the window updates. So let's talk about app, because app seems to be very important, right? And it is. It's how everything comes together. The Bevy app crate is the sort of high-level single pane of glass interface through which you access everything else. And as we'll cover in a second, it's also not the most important thing, right? Because everything inside of Bevy is kind of separated out and modularized and stacked at a whole bunch of different API levels. So you don't need app to do everything, right? It is the point of like single pane of glass, but like there are a whole bunch of crates that you can turn on and off depending on what you need. You can use individually depending on what they do. Some of them you won't want to use individually. Some of them, like Bevy ECS, you can use without the rest of it. You'll want to turn like Bevy UI on and off. Time is a thing here, et cetera, et cetera. Which brings us to features, right? Short side note, every one of these images is a Bevy app word game on every one of these heading slides. So Bevy by default comes with a whole bunch of features enabled. Some of these are crates. You can read them right off, Bevy Winit, core pipeline, PBR. That's a bunch of rendering stuff. Even the asset system, audio, is a really common one to turn off. There's a third-party crate called Bevy Kira Audio. So you would have to turn off this Bevy audio feature to like properly use Bevy Kira Audio. And this is sitting inside of Bevy, inside of the Prelude. Like you don't even get access to these if you start turning these features off, right? They're just gone. This is one of the really powerful things about Bevy, right? You get to, if you need to, just take a chunk of it, get rid of it, and replace it with something else. So I want to talk about systems, but to talk about systems, we have to like talk about ECS and what it is, and like why these three letters matter. This is the statement in the docs. I've chopped it up a little bit to fit on a slide. But if you can find me a design pattern that doesn't have the description of encourages decoupled, you know, whatever that breaks up your app and data logic, I'll give you a cookie. I don't know. They all say this, right? So like, and then there's something about, you know, parallelism and performance and whatever. This is kind of how I would describe it. Bevy's ECS specifically, but ECS in general, enables working with only kind of what you need when you need it. So if your players have lives, right, and you need to remove a life, then your system only needs access to the lives count for those players to decrement them, right? If you need to move, you know, a laser from a ship across the screen or the player across the screen, you don't need access to, you know, the player and the dog subclass and the whatever, right? You don't need this huge inheritance chain. You just need the transform of the player and the input controls. So ECS, long form, Entity Component System. If you've used Bevy, you've probably seen this. If you haven't used Bevy, this is probably meaningless to you. Entity is literally a U32. Like there's nothing more really to that. Well, there's a little bit more to that. It's a little bit of a lie. But an entity is an ID, basically, right? Components, data, structs, enums, just things that are, you know, stateful. Systems are regular functions, and that's super important, actually. So let's go for entities first. So everything gets an ID. Everything is an entity, or, you know, most things are entities. The IDs are generational, so you actually get a tuple of 2 U32s. You don't just get one. And it's almost like a vec, right? So imagine that you stored everything in your game in a vec, that each of them existed at some index, and then like the thing at index 3 died and you removed it. Then you spawned something else. It went into the index 3 slot because index 3 is empty. How do you tell they're different, right? That's what a generational index is. So index number 3, version 1, or index 3, version 2. That's it. Those are the two numbers, literally. Components, state and data, things like how much health your player has, whether they are the player or not, right? They don't have to carry actual data, they can just be tags. How fast they can go, the speed, the type of the enemy can be an enum. You only get one instance of each component type for each entity, right? So it can't be a ghost crab or a skeleton crab ghost. You get one of them. Systems, regular Rust functions, they operate on components. The dependencies are supplied by Bevy, which is one of those really, really important ergonomic choices. So here we've got this function. We query for all the transforms in our world, basically. And then we multiply the y by 2 every update for all the transform components. This is the sort of app that I pulled those 2 examples from. So we've got app new. We've got a couple of systems added at different times. We haven't talked about startup update, post update yet, we will. And then we run it. So on startup, we spawn in an entity that has a transform component. We spawn in that entity at 111, arbitrary location. Every update, we multiply that y value by 2. And after every update, on post update, we're just printing everything out. So you can see here, if it's not too far bottom left for the people in the back, basically entity 0, version 1. That's the entity ID. That's what we just talked about. And then we've got the component for that entity that has a translation of x1, y2, z1, which is exactly what we just had. So we're spawning an entity. We have a system that queries for all transforms or all entities with a transform, gets us those transform components, we mutate it, we move on. So the fact that we can use regular functions as systems is a really important ergonomic choice for Bevy. Because we write a lot of them. Like, we write a lot of systems. That's how all of the logic is written. So you're going to be writing a lot of functions. If they weren't regular functions, if they were some like weird construction thing that you had to do inside of main or whatever, it would be really annoying. Here we've got laser movement. It's another system. Queries for all entities that have both a transform and a laser component that identifies them as a laser. And then we get time as well, because deciding how far a laser moved either gets tied to the frame rate or tied to the amount of time that has passed. You want the time that has passed, not the frame rate. Otherwise, that kid with the 4090 is going to be moving a lot faster. And thus, lasers move. That system is all we need to move lasers across the screen. So this ship fires a laser, it just keeps going, and it keeps moving, and then it goes off the screen and disappears, and we don't respawn it. So that could be super generic. It could have been linear move, right? Instead, it was laser. This is generally dependency injection. Dependency injection is a little bit complicated, so we're not really going to get too deep into it, but here's a couple links. This sort of book, Dependency Injection like Bevy from Scratch, is really great. If you are going to go implement this kind of system, definitely go read it. Axum does a similar thing with from request, and we're going to talk about system params. But dependency injection at a high level is just passing arguments to functions. This is the system param trait. Don't get too hung up on all, lifetimes and trait bounds and whatever. There's some state, there's an item. We can initialize that state, we can get the item. That's really what I want to get across on this slide. As a user of Bevy, you never really see this trait. Like, you'll never ask for a system param explicitly, unless you're writing a library that does something special. This is a list of system params that are common in Bevy. We saw query already. We can query for components. We actually saw res, which is resource, which is for global data that we'll cover in a second, and then res mute, which is for mutable resource. Local state is local. Commands are how we mutate the world. We saw a capital W world when we looked at app. That is kind of like everything. It all sits there. And then we've got event readers and event writers. How a function can turn into a system is a giant stack of traits, traits that can be implemented in various ways, a bunch of intos kind of traits as well. The system params, a couple of macros. It's pretty deep, honestly. So if you're going to implement a system like this, this is an industrial strength version of it, but I'm going to go tell you to read the code because it doesn't fit on a slide, or two, or five, actually. It could be a whole talk in its own. So what we're going to do instead is talk about all these system params and a little bit about how they work and what value they provide. So let's start with global state. Resources. Typically, in a Rust app, for global state, you do something like const, maybe static. Because we have this app, because we have this world that contains everything, we can just create this resource. We can get this resource anytime. And we're only allowed to have one. So that's enforced. This is both a great example of what I was talking about earlier in that everything can decompose. So you don't need app to be able to insert a resource into the world, right? App has insert resource in that builder. But we don't need it if we just have a world already. So we've got this resource struct. We have to derive resource on it. It's just a U32. And we've got two systems here, one that reads, one that writes. Then we've got local state. So we've got global state and resources, and we've got local state with local. This is the same example we saw earlier, only slightly modified to not have .run anymore. Because .run is only running for one update, and I wanted to look at two. So this is app. We add our systems just like before. Remember, we're getting mutable or exclusive references to this app, so we can do this kind of however we want. Those references can drop anytime we want. We just need the original one. And then we call update twice instead of calling update once. So at the bottom, what's changed in this example is that instead of just having one output, post update has run twice and update has run twice, but startup has only run once. So we get 121 for our translation, and then 141. I did just have to look at that instead of doing 2 times 2, yes. So if we cut all that back, we get our prelude, our app, we're adding a system and update, and we've got this onUpdate system that has some local state. Local state gets initialized to whatever the default value is, effectively. It's not quite exactly that, but it is that. So we get basically the number 0 the first time this runs, and then we're just adding 2 and adding 2 and adding 2 and adding 2. So every time this runs, and you can see here we're doing a loop, so we're just calling update, calling update, calling update, right? We're just manually iterating frames here. We're doing next frame, do the next frame, do the next frame. And since we're only adding numbers, it runs really fast. And we're just debugging that out. So you can see how the state increases over time because this function is running over time, but the state doesn't disappear, right? And you can't access that local state from any other function. So it is local. This is the implementation of system param. Again, don't get too hung up on this. This is about the simplest implementation of system param that you're going to see. Query and other things are much more complicated. They don't fit on a slide. That's why we're looking at this one. But, so we've got some type T. In our case, it's a U32, like we were looking at with local before, right? So we've got sync cell T and local T. We initialize our state, which uses from world. I want you to read from world as default because it will call out to default if there's a default implementation. It's basically default with access to the world, but that's not super important. So imagine this is just the default value getting wrapped in a sync cell. We get the param, and when we get it in the actual system, what we're getting is state get. So we get our U32. Query is another thing that implements system param. This is how we access all of our component data, right? So in this case, we've got system query. System query introduces another 2 new traits. There's a lot of traits in Bevy, like a lot of traits. So we've got query data and query filter. You can iterate over queries, iterate over the components. And the key thing I want to drive home here is that these are basically small little databases, like ad hoc databases that you've constructed. Like fetch me all of the items with these 2 components that also have that thing. And then iterate over them or do whatever. Or more specifically, these are the things that you can put in the query data slot, which is the first slot. These things are implemented for a large number of tuples. You can effectively have like infinitely nested, like super complicated, well, not super complicated, but like it's just like nested tuples infinitely, so you can get as much data as you ever wanted. Don't nest it 16 times. I don't know. That would not be great, but you can. So we're querying here for entities with a player and a score. We're getting exclusive references to them, or at least for the score. We're getting a shared reference per player. And right at the top here, you can see that references implement query data. That is what that means. That means that you can put references there. You can put entity there. You can put option wrapping one of these there. And then we're going to skip the other 3 because they're not super important. Query filter is also very interesting. So we've got query data, right, which is this data that we want to get back. And filter filters down that query. So in this case, the top query is filtering that query for transform and player ship type by only the ones that are tagged with player. This becomes more important when you start building plugins and looking at like added and changed, because you can offer really ergonomic, like here's a component that you can add to your thing. And whenever that is added, right, whenever we use the added filter in our system, in our plugin, we can do all of the initialization inside of our plugin, right? Take this component, put it on your entity, whatever that entity is. If you're doing, let's say, a camera, right? And you want to do a 3D pixelated view with a tune shader and a post-processor on that camera. The user only needs to slap, pixelated camera component on their camera component, and then your system has added for pixelated camera component, and then you do everything you need to do. Hide it all away from the user, let them configure it through the component, be done with it. It's a very powerful pattern. Again, queries are kind of like databases. We can iterate over a whole bunch of stuff. Just checking my own time here. We can iterate in parallel, we can iterate in combination, we can do a bunch of different kinds of iteration. If there's only one of them, we can, kind of do the unwrap thing or, return an option, or actually it's a result, if I remember correctly. But the most important thing on this page is get, right? When you do queries for all of these entities or all of these combinations of components, you're going to get what is effectively a key value store. If you have an entity for any other reason, if you stored an entity in a resource, like you say, this is the player's ship, whatever it is. This is the inventory bag, whatever it is, and you have some entity, you can do the query for all transforms and then do query.get with that entity ID and get just the transform from that database for that player. Commands, another thing that influence system param. These are mutations, world mutations, right? One really important thing is that they're deferred. So they're not instant. You're not saying commands.spawn whatever and getting the thing. You have to wait for it to be applied later. This happens in another system. You can put this system anywhere in the system order that you want. In this case, we're looking at spawn. So spawn spawns an entity and then associates a component with it. In the first example, we spawn an entity, associate component 1 with it. Bundles, not really going to cover, but they're basically collections of components. So this is spawning an entity, associating component 1, component 2. Spawn an entity, associate component 1, component 2, then also insert strength and agility, then also insert label. So you can chain them, and then they get applied later, right? So you can't do commands.spawn and then expect to have the actual thing, but you do get the entity ID if you want it. Events. Events are actually super important, right? So we talked about a bunch of stuff. It's very easy to be like, yeah, components are important, right? Like components are everything, right? Components are all of your state, it's the health of your player, it's whatever. It's easy to ignore events, but events are the way that you can decouple all of these systems. They're kind of the way that you don't get these massive amounts of systems or like systems that need everything, right? In this case, we've got a system for sending events, system for receiving events. We've got .chain here, which we haven't really talked about yet. This is forcing an order, so one has to run then the other. By default, it's in parallel. We add the respawn event, and we do one update. So respawn event right at the bottom, we derive event on it, we've registered it. In send events, we can send as many of them as we want. Just keep respawning the player. Never let them step out of the spawn. Just keep respawning the player. And then we've got receive events. In this case, all we're doing is printing them out. So we've got the first one, the second one, the third one. The one thing I will say about events is if you want to read them in the same frame, they have to come after they're sent, right? So you have to send and then receive if you want all of that to happen in the same frame. It doesn't have to. And this is a quote that actually happened half an hour ago. And I went, wow, that's such a great quote for this point in the talk. And I added the slide. So events are what let you have systems that don't grow into huge unmaintainable monoliths. And what this means is effectively, if you have a system, right, and it's dealing with meteor collisions, what do you do after the meteor actually gets hit, right? Do you then spawn everything and despawn everything and then manage your assets and like which sprite needs to be there and like what animation is going to play, or you just fire an event and let some other system handle it? The answer is number 2, by the way. Schedules. Schedules are kind of like the way that you add systems to things that will actually run in some kind of order. This is a schedule that runs a system once. This is the list of actual steps in the Bevy cycle, effectively, or the schedule, right? I'm trying not to use the word schedule to define schedule, you know? We've got pre-startup, startup, and post-startup. We saw startup already. It runs once on startup, right? And we've got first, pre-update, whatever. We've got update in there as well. That runs like every frame. You can write custom schedules, and people do, right? It's really powerful to be able to do this. This is probably what you're going to be dealing with if you're just writing your first Bevy game. You're going to do this, you're not going to write a custom schedule, you're just going to add to these schedules. There's a thing called schedule label that's super interesting that we don't have time to get into, but I did want to point it out for the people who care. And then I cut off rendering right at the bottom on purpose. Rendering is a whole other app, it's a whole other sub-app, which is a app, but you know, inside of the other app. I know that was very great. But basically, rendering is a whole other world. Like you can have app 1, and then you can have like app 2, and rendering is app 2. So we kind of like, I cut that out of this presentation because it's actually too long. So plugins then, right? And this is kind of like where the loop starts to connect. These form a critical piece of infrastructure, and they're powered by this app, right? This app is always valid. This app is this builder. This app gives us so much configuration. This app lets us add whatever we need, add all of our systems. Our systems are able to selectively query for what they actually need. We don't need to care about what people are actually doing. When they have a certain component, our system can query for that component. We can let people configure our plugins. And this is the like easy path plugin, right? And the thing that I'm kind of getting across here is that plugins are not just something that somebody else wrote that put up on crates.io and that you installed and like enabled physics for you, right? Just as an example of a really complicated kind of plugin. Plugins are a way that you can actually structure your application, right? When you're writing a bunch of files, you probably started with just a main.rs, right? It got a little bit more complicated. You decided you wanted to add some tests. Maybe you added a lib.rs, right? Maybe you started adding more modules, right? More files. Plugins are kind of like the next step after that, right? If you've got a bunch of things that have good boundaries, put them in a plugin, let them be isolated, test them in isolation, add that plugin to your app, and you don't even need to change your code really, right? Because like when you write a plugin, you're just getting app anyway. So main.rs has an app, it's doing some configuration, it's going to add this plugin is going to also do the exact same thing that you just did and configure app. So like there's this loop that happens, right? In that app is super important, and the way that you configure and run and access Bevy apps is the same way that you do it with plugins, is the same way that you do it in all other respects. This is the list of the default plugins. This is like the, like plugin prelude, If you are going to start a new Bevy app, you probably want this stuff because you probably don't want to deal with picking and choosing what you want. You probably don't even know a bunch of these exist, honestly, right? Like the Winit plugin that we talked about earlier. Right now, we don't have one in our examples, so it just runs once. But you need like a window at some point, right? So like, do you want to go to the docs and figure out that you need a window, or do you just want to add the default plugins? So Bevy uses plugins to build Bevy, which is really interesting, right? Like we talked about with the audio stuff, right? Bevy audio might not be what you need. You might want Bevy Kira audio. So you have to be able to disable that plugin entirely and insert a new one and have that work, right? Like actually work, not just be kind of hacked together, not just be like, hey, we're ignoring some stuff for no reason. Plugins can use resources that are added in other places, things like that, right? This is a clear color. What that effectively means is there's a camera in your game. When it doesn't need to render anything, what does it render? It renders this color, which is like a little bit blue. One thing that's difficult about plugin systems in other ecosystems is how do you, like, if you have this default plugin set, but you only need to change like one little thing, how do you actually do that, right? How do you reach into everything, change that one field, and then not touch anything else? This is how you do that in Bevy. So plugin groups implement this .set, and you can just completely replace the window plugin, and in this case, it's a game about space. So the window title should say space. Again, progressive disclosure of complexity here. Build gives you the app. It can be just what you wrote in your main.rs. It doesn't need to be fancy. It doesn't need to be complicated. You don't need to have gone to have a CS degree. It can just be that kind of like spaghetti code that you were writing, moved into a different location. But if you do need something better, you can opt into a bunch of these other extra functions, right? You can do async work when your plugin initializes, and then tell Bevy when it's actually done so that you can actually move on. We'll talk about a crate later that does that kind of thing. So we're going to lighten up a little bit here and talk about a couple of smaller traits, deref, deref mute. New types. I talked about earlier how Bevy only allows you to have one instance of a component per entity, right? If you insert an F32, you can't have any other F32s. Hence, new types. Wrap your F32 in some struct. Unfortunately, what that means is that you have this little .0 sticking around everywhere in your code base. I don't like that .0. Bevy includes derives for deref, which means that this .0 just goes away. It's really nice. A little quality of life improvement, right? Talking about ergonomics here. Deref mute, also in Bevy. So the last one didn't work for mutable stuff. This one works for mutable stuff. 0 gone. No more syntactic eyesore. Default, another small little quality of life improvement, right? Bevy has a lot of structs. There's a lot of things in games. There's a lot of things that have a lot of fields that are very, they're just very configurable, right? So you end up typing default a lot. This is some UI code. It's got some button bundles, some image bundles. If you've ever written CSS, you know how many different rules are applicable to like any random DOM element. It's the same kind of thing here, right? Like I don't want to type 50 fields, you know? I want the 2 or 3 that I care about. And then I'm going to write default for everything else. So I write default a lot. So when you import the Bevy prelude, these two are the same, right? In regular Rust code, you can get the default trait, spread it, struct update syntax. In Bevy, you can do this. And it's really silly. Who said generics weren't useful, huh? So if T implements default, then call default. That's it. There's nothing more to say about that. You just get the thing, and it is the default implementation. It's actually quite nice. And there's a lot of these little things, right? Little ergonomic things. We're going to talk a little bit about materials. Material is actually why I wanted to write this talk in the first place. Unfortunately, there's so much to talk about in Bevy that I didn't get to go on a deep dive into rendering. I'll have to do that in another talk. But material here, right? It's another trait that Bevy offers. If you've ever written GPU code, if you've ever written shaders, if you've ever tried to use WGPU or WebGPU or any of these other, graphics APIs, they're extremely verbose, right? You have to write a lot of code just to get like a triangle to render on the screen. In this case, you get a bunch of these functions that you can implement. They have to return basically this string. So this is all of the code you need to initialize and use a custom shader for a material for a cube. In this case, we're defining the data that is actually going to get sent to the GPU, the data that you're going to send to the shader. It is just a struct with some derives on it. Really nice compared to, manually setting up bind groups. The fragment shader is the only one we care about in this scenario, right? Maybe we want it to render red instead of blue or, whatever. So we just point to our WGSL script, and that runs our fragment shader. We get material plugin, which we're going to talk about a little bit more deeply in a second. That sort of like sets up the ability for this material to exist. And then we actually get the usage. Material mesh bundle, we're spawning a cube, we're using our material, we're setting our data. If we want to, we can update all of that data in systems. If you wanted this to be flashing rainbow which, like, who wouldn't want it to be flashing rainbow, right? You write a system, you get this mesh struct, and then you just change that color value. This is the material plugin. It's got a lot more code than you actually wrote to even implement the material, honestly. It initializes resources, it adds render commands, it initializes more resources, adds some more schedules. These are all things that are like generically applicable to any of your materials. And it would not be great if you had to write this instead of what we saw on the last slide, because this isn't even everything that you need to write. And again, there's a whole sub-app, right? That happened in the render app. That didn't happen in Bevy's core app. So you would have needed to know about the render app in the first place, and then also figured out how to get to it, and then also added those plugins and stuff. And this kind of like, if you care, it's here and you can go do it. But if you don't care, you've got these high-level APIs that like ease you into just what you need at the time that you need it. Which is Bevy, for me, for this talk, this is what I want to get across. Bevy is the progressive disclosure of complexity. There is a bunch of high-level stuff, there's a bunch of mid-level stuff, there's a bunch of low-level stuff, and there is that for every vertical stack that you can think of, right? For UI, for rendering, for materials, for dealing with components and transforms and whatnot. Bevy is extremely extensible, right? If you want to dive in, you want to implement your own system param, you don't like the way query works for some reason, you want something else to happen, you can do that. And it just works. Just implement system param. Query data, query filter. You can implement your own filters, implement your own query data, implement your own materials, we just saw this. Implement your own commands, things that mutate the world. If you have a bunch of logic that you want every time you spawn a new flying saucer in your game, implement a command to deal with that. Then all you need to do is commands.add in your system instead of, find the sprite, choose a location, find this other thing. Schedules, we talked about schedules. You can do custom schedules too, right? You've got, update and whatever, but like maybe you're writing a physics library. Maybe you need like a custom schedule. Maybe you need it to run at specific times. And you don't want the user like futzing with it, right? Make your own schedule. There's also the render graph. This query data derive shows off sort of like abstracting queries themselves, right? So you can even go deeper, right? You can write a whole bunch of queries, you can keep everything manual, specify everything, or you can derive query data for your own struct. Everything inside of this also derives query data, so it just works, and you get everything. And now you can type my query when you query instead of all of these other things. I want to finish off talking about a couple of crates that do these kinds of things. Crates that would be useful to look at if you're looking at implementing any of these APIs. Bevy Asset Loader implements its own schedule, builds on top of assets and states and schedules, things like that, to configure highly configurable loading of assets. And it just fits into everything else, which is super nice. And now you get a loading screen that actually ends when things have loaded, right? ASPerf UI is a new one that came out, I don't know, like a week or two ago. Configurable debugging implements system param to power itself. It's this thing on the right. Super configurable. There's a whole sort of level of abstraction for like sending data into this. Bevy ECS tile map. Every entity is a tile, which is kind of like wild to think about because like that sounds like a lot, right? But Bevy ECS tile map dives into that sub app that we talked about before, right? Dives into this render app and actually creates its own render pipelines to optimize all of that rendering and deal with it. And you don't have to care, and you get an entity for every tile, which means you can animate individual tiles, which means you can build that mining simulator where your little thing hits that brick and it, destructs a little bit. Relationships in ECS are not built into Bevy currently, but they are built into this, which is a third-party ECS relations crate. That is very cool. Builds on top of query data, query filter, world query, things like that. Nanu, creative coding framework in Rust, used to be completely independent, is now rewriting in terms of Bevy plugins. Ongoing work, so I'm not going to talk about it too much. I don't want to commit them to anything they haven't actually committed to. But very interesting that this is happening because it means that they don't have to maintain their own rendering, right? It doesn't mean they don't have to maintain their whole own ecosystem. They can build on top of Bevy. So, the end, Bevy is the progressive disclosure of complexity, the ergonomics of the APIs. When you look at it, actually is a bunch of stacks of different APIs at different levels, going from the basics to the expert to everywhere in the middle. We didn't talk a lot about actual game development today. I do have a game if y'all want to see it, but otherwise, I think that we are good for. Okay, let me show you a game. Let me mirror here. Is that showing? Yeah, great, cool. Asteroids, basically anyway. This is Bevy UI. You can click stuff, spawn in some world, or spawn in some ship, right? We talked about this earlier. Lasers going forward, things different spawning, events. One thing notable is that it wraps around, right? I know the game is not super interesting, but the way this is implemented is. So I've got this movement plugin. I add systems to the update method. There is linear movement, which accounts for meteors and lasers. There's spin, which is only applied to meteors. And there's wrapping movement, which is applied to anything I want to wrap around like we were seeing before, which is meteors, ship. Maybe you have a boss that you don't want wrapping movement on. This component is the API, right? Linear movement, where is it going? How fast should it move? And then linear movement is like a relatively simple system, right? It is a query that looks for transforms with the linear movement component and the amount of time that has passed, right? We need to be able to figure out where we're going and how far we're going. We don't actually care what it is that's moving. Doesn't matter. Meteor, ship, laser, doesn't matter. It's moving in a line that way. So all we need is the transform. All we need is how fast it should go, which direction it should go. Same thing for the others, right? Spin is the same way. Query for the component, spin it over time. Wrapping movement, very similar. Query for anything with the wrapping movement, and when it goes outside of the screen, move it to the other side. Is this the meteor file? No, it's not the meteor file. So meteor bundle, meteor types, meteor speeds. We're spawning here. Bunch of different stuff, bunch of those components that we saw earlier. So I can add these to anything now, right? In this case, the meteor has linear movement and it spins and has wrapping movement. But if I didn't want it to have wrapping movement later, I just remove that component, which I can also do at runtime. The other thing I want to mention here before I kind of close this out is if you can't delete code, then you're stuck with it, right? And the way that these systems are set up, right, these little systems here that operate on just what they need to, are really easy to delete. If I want linear movement to behave a different way, I delete that and I rewrite it. I don't care. It's 20 lines of code, right? And you don't want things that are 50 query systems, right? You don't want everything to come in. You want things like this. You want to be able to just delete that, change it. And that's the talk. So thank you.
Questions?
somebody right here.
Hi, thanks. So I have made an unfortunate decision to make a turn-based game in Bevy.
Yeah.
My third attempt so far since Bevy like 0.6 or something.
Sure, yeah.
Love all the recent changes in Bevy regarding inferred sync points within the schedule rework, the system registration. It makes it all easier. The one-shot systems. But I still feel like every time I register a system, I'm afraid that I'm not thinking about registering it in the correct order regarding other systems, like that my system is after one input, but not before the events. My event handling is before event sending, and so on. And every time, and as my plugin grows, I'm more and more afraid about specifically the ordering of the system. And I think, do you have any thoughts, suggestions, or opinions regarding how to structure the ordering of systems within the app?
Yeah, so first of all, the ECS and Bevy itself, doesn't sort of cause that issue, right? You need to care about the order if it matters, no matter what kind of system you're using, right? No matter what engine you're using. I think that when it comes to the events, like I said earlier, right? If you want things to happen in the same frame, then you have to send before you receive, right? If you don't need to care whether it happens in the same frame, like a turn-based game might not care, right? You might not actually matter whether it happens at the end of this frame or the beginning of the next one. And if you can make it not care, that's better, right? Because then you don't have to care. But otherwise, if things are actually interdependent, you can either start creating your own schedules, right? Or they are actually dependent and they should be next to each other, right? So you can do things like dot chain, right? You can do things like dot after, dot before. It's fairly easy to go from parallel to ordered, as long as you're not trying to keep things so far away that they don't talk to each other, even though they're actually dependent on each other. Somebody in the back over there, maybe, and then we'll come up to the left.
There's a large community and passion for Bevy at the moment. The thing that surprises me the most is the amount of changes for every version. What is it, in your opinion, that keeps, the passion for Bevy, despite these breaking changes being so, at times, drastic?
Yeah, so when I think about Bevy right now, I think that it is going to be, so obviously it's pre 1.0, right? It's right there in the Semver contract, going from 0.12 to 0.13 might break stuff. Second thing, you don't necessarily need to upgrade, right? 12 to 13 is not going to make or break your game necessarily. It's always nice to have new features and to get onto the next version and whatnot. But some plugins don't even update for weeks or months after a release happens. As for what keeps my passion around, I think that my passion for Bevy currently is related extremely to my passion for Rust. Rust kind of enables me to do more than I could before, right? It enables me to write web servers. It enables me to write UI in the browser. There's another talk on WASM that's happening right now by Ben on Leptos, which is wonderful. I can do embedded work with Rust, right? And I can do games, and I can do, if I wanted to do kernel development, I could go do kernel development. So I don't trip myself here. So that's kind of the thing that really keeps me interested in Bevy. It enables me to do more and more. It's like this material abstraction happened in 0.8, right? And it wasn't perfect in 0.8. And shader changes have happened over those versions from 8 to 13 that have been breaking, right? But the fact that it just keeps getting better and isn't just breaking for no reason is a huge benefit, right? When I upgrade from 12 to 13 or 11 to 12 or whatever, I know that what I'm getting is a better result and it enables me to do more stuff, right? In one of these releases, we got deferred rendering, right? So if I wanted to do 2D lighting, Now it's easier for me to do that, right? Meshlets are, I think they just got merged. I think I could say that. They're behind an experimental flag, but if I needed to do something that was very geometrically dense, and that PR wasn't merged, I wouldn't be able to do that. So like, when I think about how sort of passionate I am about Bevy, it is getting better, right? It's not like the changes are breaking and I'm going, why am I even updating this?
Speaking of turn-based games, the way that Bevy is set up is that usually you do one update per frame at least. So nowadays, things are getting more mobile than ever, so battery is of course an issue there. So is there a way to just switch this off for a while, perhaps until the next event or until some time has passed, and then activate it again?
Yeah, so I didn't really talk about it in the talk, but Bevy is also built to be able to power things like desktop apps, things like a 3D modeling app, for example, like a Blender or something. You don't want Blender just like constantly spinning all the systems all the time, right? So like if you mouse out, it should be able to like power down or whatever. I don't necessarily know how that translates to mobile specifically, but there is stuff in Bevy for handling that power management, for handling like the entire app will basically pause depending on how you configure it. I think we have somebody right here that had their hand up. So it's hard to see people in the back, so if you have a question in the back, please do raise your hand very high.
Hi, I really like this quote, progressive disclosure of complexity, and I've kind of tried to express it when I've onboarded people I know to Bevy, and haven't had a concise way to say that, so that's very helpful. So I appreciate that. But my question has to do with sort of education in the Bevy space about ECS, because I still find that when I do onboard people who aren't familiar with ECS paradigms, they get very confused by things like expecting that component data is present on the entity data type, or not understanding the purpose of a query. And these things, while like, for example, your YouTube has a lot of content that provides information on this stuff, I don't think those are very discoverable from like a Bevy starting point, right? What do you think Bevy's path towards having better educational content available looks like? Is that something that they're, as far as you know, focused on in the near term, or I guess, what do you think they like need to do in the nearest term to solve that problem?
Yeah, so Bevy actually just got a foundation like last month or a couple weeks ago, or time is, I don't know what time is anymore. But Bevy has a foundation now, which means they can like hire people, and Alice is one of the people they hired and are now paying, hopefully. I don't know if they're actually getting paid right now, but they're going to get paid. They're going to get a salary. And they are focusing as one of their tasks, I believe, on the Bevy book, and like the next generation of the Bevy book. So I think they're aware of this. They already know about this. The reason there isn't more like written, tutorialized documentation in Bevy right now is because it is extremely hard to keep up to date. As somebody that does do that from version to version for a bunch of workshops and things like that, it is an immense workload. And they're focused mostly on making the engine better right now. There is documentation. That isn't to say there isn't documentation, but it's like documentation in the APIs and the reference, and it's not like, how do you make Space Invaders, So I think they're aware of it. The Bevy book should be a great boon to that. The Bevy cheat book, if anybody isn't aware of it, is a great resource. One of the staples of the ecosystem, honestly, personally, I think. But yeah.
2 more questions. There's one. One at the back.
One in the back. Sorry, with my glasses, it's glary, so I can't see anybody back there.
The ECS system in Bevy pushes a lot of problems from compile time to runtime. So for example, if you forget to create a resource, but you're still asked to use it in a system, you get a runtime failure rather than a compile time failure. Can you see any ways to address this in the future?
Just like in general? I think like right now, if you are expecting something to exist and you want people to like be aware that it needs to exist in the system, you can make that optional. And if it doesn't exist, throw an error or a warning, right? I don't know that that necessarily helps with moving it to compile time. And I don't know if the, I don't know what the current thinking is on moving more stuff to compile time, because ECS is kind of like a, like you said, more of a runtime like pattern. So I don't know, I'm not sure. I would have to look into it a little bit more. I would say that if you're concerned about it and you're providing APIs, make things optional, warn, throw errors. You can do things in development that don't happen in production, right? So like you can make sure that those resources are added when your systems run, when the development is happening. That would be my suggestion currently.
Last question up front.
Hi, I have a weird question. So one of the reasons why I love Bevy is due to how modular it is, and not just like how composable things are when you're making Bevy applications, but also some of the crates, in my opinion, are very useful outside of Bevy. And one that particularly comes to mind is Bevy Reflect. And it kind of saddens me that it's like the probably best reflection crate in Rust ecosystem, but it's not widely acknowledged as such. And maybe there are like plans to, I don't know, like market it in some other way or even extract it from Bevy so it becomes like an industry standard, kind of like CERDI and other crate maintainers implement reflection traits for their tags.
Did you have a question at the end of that, or?
Yeah, maybe like, I mean, are there any like plans to see some parts of Bevy in like a bigger scope than they are right now?
I think like the Bevy project should always be focused on kind of like Bevy first and foremost, right? Like if you, it would be really nice if the Reflect crate turned into something that was widely used and the entire ecosystem depended on it. But there are definitely trade-offs with that happening as well, right? Like if everybody is using it, you have to support all of those APIs and all of those users, right? There's this kind of saying that goes like Semver is kind of for people who don't have enough users yet, right? Like if you have users and they depend on the way that your library works, kind of like any change is breaking, right? So, I mean, there's trade-offs to that. I would say that if you think that it is that strong, that it is that important, that you start writing about it. Because you ask somebody who creates content about how to get the word out that this is a great crate. And if you feel that way, you should write about it and tell people. And I think that's the way the word gets out, honestly.
Please give Chris a massive hand. We're now going to have a refreshment break before our last keynote. So please head to the exhibitor lounge for some refreshments before we come back and finish the day. Hello, Rustation. How you doing? You been enjoying the sessions? Great. It's been a great day. I am very excited to announce our final keynote. Someone who has been maintaining a key crate that has been a part of many of your projects, I'm sure. Please welcome Alice Rill.
Hey everyone, thank you all for coming. It's been a long and nice conference with lots of nice talks, but now we are reaching the end. So I'm going to talk a bit about Tokyo and, open source. So who am I? My name is Alice, and I am a core maintainer of Tokyo, which is an asynchronous runtime. So those of you who have used async Rust, you've probably used Tokyo. That's a pretty good chance. I also do some other stuff. I work on Rust in the Linux kernel, on the Android Rust team at Google. So yeah, all this awesome stuff. But I want to start off by telling you a bit about how did I get into open source? How did I get into Tokyo? And for me, it really all started with, I was helping people on this forum. We have it's the official users Rust forum. I spend a lot of time there helping people with their Rust questions, all sorts of different things. I realized that I was helping a lot of, there were a lot of Tokyo questions every so often. At some point, I joined the Tokyo Discord and started helping people there. So I was helping all of these people. I saw what they found to be confusing. And so my first PRs to Tokyo, they were doc changes. Yeah, and so when I started, what I really cared about was, this documentation, like these users, what if they had a nice experience? And so this is my first PR that's not a doc change. Even this one was, some users asked me, oh, I have this hyper stream of bytes, and I want an async read. How do I do that? And my answer was, it's kind of difficult. But no longer, because I added a utility to do that. So even when I started, submitting features, it was still motivated by the same idea. This idea is that I talked to users, and we improved things to make their life easier. So one thing I really like is this idea that when you've seen a question a few times, maybe you should do something about it. So one example of this is my first successful blog post, this what is blocking? This was a question I got a lot of times, and every time I had to answer it, it was like, oh, it's a long story, And so I wrote a blog post. Now my answer is not so long anymore, it's just a link. If you haven't read it, you should check it out. The takeaway is that async code should not spend a long time without reaching an await. Other documentation things we've done, feature flags. Tokyo is, it's one crate. It used to be many crates, but now it's one crate. But we still have feature flags, so you only have to compile the things you need. But sometimes, if you're trying to use something you haven't enabled, you just get an error saying, oh, this thing doesn't exist. I think the error is better today, actually. But still, we added these special markers to the documentation saying, oh, if you want to use this, you need this feature. And this is a small thing, right? But yeah, I think it really makes a big difference, like all of these small things. Another thing we documented, select is kind of a long story, but one problem we had with it was the features you use it have to be cancellation safe. And so I went through every single Tokyo function and documented whether it's cancel safe. Then, we put together a tutorial. This wasn't just me, it was also Carl. But we put together a tutorial, and this was actually back when we were releasing Tokyo 1.0. We wanted to make a crate that people could rely on, people had good documentation, and some amount of stability so that the entire ecosystem doesn't have to go update every time we make a breaking change. That's not so nice. So this is from the blog post that announced 1.0. And so we wanted to say, we're going to promise not to do a 2.0 for some amount of years. And we still have no plans to do that. If it stands to me, then we will never do that. And I thought it was kind of funny that Nico at the opening keynote was talking about stability without stagnation. If you read the last line, the stability does not mean that Tokyo will stagnate. We still have a lot of work to do. So that's also something we care about. Now, so we released Tokyo 1.0 on December 23rd, 2020. And then 2 days later, we get this issue saying, hey, your read-write log, it actually has a soundness issue. There's some unsafe code in there that's wrong, so my safe code causes memory unsafety. And we thought, damn, we just promised not to do breaking changes for several years. But sometimes you have to be pragmatic. We said, okay, people have only used this for 2 days. If anybody has started using this yet, they probably have it fresh enough in their mind that they can, go change their code. And we removed the problematic piece, and then we had Tokyo 1.0.1 with a breaking change. And I think this is kind of interesting, right? Because, projects say, we're not going to do breaking changes unless it's, a major version bump. But, sometimes you do something that's technically a breaking change, but, not all changes are equally breaking. Right? This was an API change. We removed something from the API. Still, it was OK. Now, we tried this another time. So this wasn't even an API change. We were just changing the behavior of one of the APIs. Right? So it's kind of, is this a breaking change or not? Well, it's not always so clear. But in this case, it turns out it was, because, I guess you can call it the scream test, right? Because we don't have telemetry. Like if you run Tokyo, it's not phoning home to tell us what you use. So in some way, the only way for us to know whether somebody is using something or relying on something is the scream test. Right? We tried this out. People screamed. We reverted it. So sometimes breaking changes are breaking. But anyways. So, I think this is kind of interesting that, things are a bit more fluid than you think. And, this kind of thing about what do you promise? Like, I think there are a lot of interesting things you could talk about. minimum supported Rust versions. Tokyo has like long-term support releases, but I'm not going to talk about that. One thing is, when you submit a PR to Tokyo, do I have to take the PR? I mean, obviously not. But, I mean, we still have to be nice to each other, right? And so, I mean, for example, if it's a change that we are never going to accept because it's the wrong direction, then we should actually think about that when we get the PR and then close it then. We shouldn't go through 20 rounds of review and then figure out we don't want this and then close it, right? Because then we wasted your time. One thing you will often see in open source projects is that before you submit a PR, if it's something you spend a lot of time on, you should probably talk to us first, right, before you spend the time. And that's because of this kind of thing. I don't like closing PRs. I like merging them. Yeah, I think this is really important. Maybe there are some of you out there that want to get involved with open source. I have a few thoughts on this. I know other talks have had thoughts on this as well, but let's say you wanted to get involved. Well, pick some project you're interested in. I'm talking about Tokyo, but there are others out there. I think most people start by submitting PRs. You can do that with issues, or if you have something you care about yourself. We sometimes, it's not that rare for us to get PRs that there's no issue for. I think that works too. And one thing that many new contributors are worried about is this thing about knowing everything. And that's really not necessary, I think, because generally code bases that are well designed will be modular. Right? We have a message passing channel, then there's the runtime internals, then there's the I/O resources. These are somewhat separate, and of course there's some relation between them, but you can actually make changes to, and people do make changes to these things without knowing the rest of the stuff. And so I think it's important to realize that you can just pick one little corner and start looking at that. Like my documentation corner when I started. Another interesting thing is this question of, who can merge PRs? And I think that, if you become involved with the project, then in some sense you want to get to a point where you can actually merge PRs. Then, that means that's pretty cool. And I think that people overestimate how difficult it is to get to that point. They think that, if we give that out to someone who has submitted only 10 PRs for a few months, then, then we're making a compromise on quality or something like that. But I don't think we are. I think that with the way we do things, we can actually, we have checks and so on to make sure that you can actually have new contributors who can merge stuff without it being a compromise of quality. So there are several reasons for this. One is that new contributors, they want to do things right, and so they're usually the strictest reviewers we have. And they rarely merge anything non-trivial, I find, without talking it over with somebody more experienced. That's one aspect of it. Another thing is that just because a new contributor clicks the merge button, that doesn't mean that nobody else will see the PR. I mean, if I see it, I will, take a quick look at the source code to make sure that it's reasonable. And if there's some problem, then we can have a follow-up PR and fix it. Right? Merging a PR is not the same as making a release. And it's only when we make a release that there's any sort of promise of backwards compatibility. And even then, let's say it gets merged, and the people who do a quick check don't notice any problems. Well, there's another check. When we actually make a release, the way we do it is, we go into the repository, we look over the log, say, oh, we made all these changes. And in Tokyo, we actually put together the changelog by hand. And then we have this PR with all these changes. And then there will be a core contributor that looks at the changelog and says, is there anything unreasonable here? And there have been instances where I merge something, and then when I submit the changelog for the release, Carl is like, actually, I prefer we didn't do that. That has happened. And so then we reverted it, and so this is another quality check. And maybe it looks okay. Then you get somebody approve your changes, and then you can merge it. Yeah, I was really hoping the Wi-Fi worked. Anyways, one contribution you can make if you're a contributor is, you can submit PRs, but there's other stuff too, right? If you submit a PR, some maintainer will have to spend some time on reviewing that. And there's actually a lot of reviewing to do. In 2023, we had 520 PRs. That's almost 2 per day on average. If you look at my GitHub Compass, you can see it over here. The majority of what I do is code review. And so when we get contributors that help with reviews, well, that actually reduces the amount of reviews that other maintainers have to do. And so in this way, it's kind of a unique kind of contribution that you can make. I think reviews, like helping with that, is kind of overlooked. It's kind of boring and so on, but at least in my case, it's something I really appreciate. Another thing, I told you about that when I got into Tokyo, I just had the thing I cared about. I cared about improving the documentation. And I think this is actually, this goes back to what I said in the earlier slide about knowing everything. I don't think you ever need to know everything to be a valued contributor. I actually find that if I look back at the contributors who have joined, some of them stay around for some months and then go away again, and that's of course fine. But some of them stay around. And I find that the ones that really stay around, they have some specific thing they care about. In my case, it was documentation. There's been another maintainer who cares about observability. We also have someone who knows about the process and signal stuff, and every time we have a pull request to those part of Tokyo, we bring him in, but otherwise he's not really involved, but he has been around for years. And so I think this is good to realize that not only don't you need to know everything, in my experience, the people who stay around, they don't even try to know everything, in my experience. It took many years until I started to know, at this point I probably know almost everything in the main Tokyo repository. But even in my case, Tokyo is a large project. We have Mayo, Axum, Tracing, Tonic, a long list of projects. Bytes, I don't know anything. I don't know all of them. There are some of them where I have never looked at the source code. And so yeah, I think you really have to think about, you really, really don't have to know everything. Yeah. Yeah, and so I want to thank, all of the people who use Tokyo, all of the people who contribute, all of our sponsors, and all of the people who download Tokyo. In 2023, we reached 100 million downloads. I think that's really awesome. So yeah, thank you, everyone.
Thank you, Alice. I also want to make a point to thank every maintainer in the room today. There are so many maintainers of so many different projects who are the lifeblood of the ecosystem, so please give them all a hand. We're now going to have our closing address, so please give Alice one last hand. Thank you very much.
Yeah.
Okay. Cool. So we've made it. We've made it to the end. We're just going to get my closing slides up now. I want to thank you all for being here. Again, I reiterate how important it is that all of you fought to be here. Things have been so hard in 2023 for everyone, and you folks made it. You asked for the budget. I've heard all of your stories about having to wrangle your management to get the budget to be here. So I truly do appreciate you all being here. So please give yourselves another hand. I just want to run through some closing slides to acknowledge some amazing people who helped make this happen. Our sponsors, they've all been incredibly amazing. I hope you've all had a chance to interact with them. They have been the people who have made this possible with their money and their effort and their time. So please give all of our sponsors a massive hand. And speaking of which, we have our competitions from our sponsors. Is anybody from Arden Labs here? Arden Labs? They were giving away a bundle, a free Rust bundle, I think, if I'm not mistaken. They may have already done that. So if there isn't anybody from Arden Labs here, whoever won that bundle, congratulations, give them a hand. I would like to ask our community recruitment partner, Realm, to come up so that they can do their giveaway. I hope all of you have been playing I don't know what it's called, but one of you are going to win a prize. So whoever was the most fastest reaction time, you're in for a good prize. Please give Jem from Realm a big hand.
Hi everyone, my name is Jem. I'm from Realm. And if you didn't know already, Realm is a specialist staffing and recruiting company. Don't all boo. We're a staffing and recruiting company with an exclusive focus on Rust and Go. We place engineers across the globe, everywhere from Sydney to San Francisco and everywhere in between, in both on-site and remote roles on a contract and permanent basis. So if you're interested in positions in Rust or potentially other languages, we can help you out. And if you're hiring, please check out our website and lodge an inquiry there. It's realmgroup.io. Okay, on to the fun stuff. So giving these away, it was a fierce competition on the Batak wall. Our winner is, please give him a round of applause, Charles Schleich. Charles, come and get him. Honestly, if you code at the speed that you hit those buttons, man, you're a productive worker for sure. Well done, man.
Thanks.
Thank you very much, Jem from Realm. Just before we get to Fastly's giveaway, is there a George Wilson in the house? George Wilson, give us a wave. We have found your bank card. Okay. Great. So come and find me afterwards. We'll give it back to you, and we won't charge. We won't charge you anything for it. We're an honest lot. Rustaceans are an honest lot. Don't worry. Now I'd like to introduce the Fastly team. Please give them a hand.
Thanks, Ernest. Hey, everyone. We're Dora and Arissa from Fastly. If you haven't had a chance to speak with us, Fastly is an edge cloud platform, and Rust. The Rust community, the last Rust language, are very dear to our hearts. We have a serverless compute platform that starts up in like 35 microseconds, thanks to you all. And we have some prizes for the ones who visited us. First draw, Arissa, if you could give that a spin, or no, I have to. So we're gonna pick the lucky winner of a Nintendo Switch. Max Tilley. Congrats, Max. You've got the Nintendo Switch. Come pick it up.
Thank you very much.
You're super welcome. Thanks for playing. Okay, and the second prize is a, oh, I can't open, don't have enough hands. It is a split keyboard, a Ferris Sweep V2. I'm going to give this another spin. James Cole. James Cole, are you in the room? I remember the brothers Cole. We had a great conversation. You're not here, so I'm going to have to pull out another name unless someone shouts right now. I can't see, the lights are bright. Unlucky. Sorry, it's like, how am I supposed to read this? James H.
Yeah, James.
James H.
Yes. Exactly.
Read me your email address. Oh no, don't read me. That's you, right? Yes, that is you. Congratulations. Woo! Thank you, everyone.
Thank you very much, Fastly, for all of the great gifts and a great raffle. Thank you for a great lounge as well. Did you all enjoy the Fastly lounge? Good. Thank you very much. So please continue to interact with Rust Nation. Yes, on Twitter. We are on Mastodon as well. If you just type in Mastodon Hachiderm, I think we're on there. You can find us on Mastodon as well. And please continue to use the hashtag, continue to share your pictures and your positive experiences on Twitter, and continue to interact with us through LinkedIn as well. The videos are up. Are the videos up already? I think we've already got some of the videos up. So if they will be up either way. The live stream has been great today, but all of the talks will be up on our YouTube channel, so you can relive all of the talks you missed and all the different tracks that you couldn't get to. They'll all be up on our YouTube channel. Just type in Rust Nation UK into YouTube and you'll find them there, or you can even, I think they should be up now, so you can even just save them now. Lots of Rust conferences this year, right? Just let's make some noise for that. So we want to share the love and let you all be aware of what's coming up in the next few weeks and months for the rest of the year. We have Rust NL, and we then have Oxidize, both coming up in May. Then we have the big one, which is RustConf, which is actually happening in September. So I'm sure I'm going to see you all there. I'm going to be helping out with that as well. So we're going to try and bring lots of the Rust Nation flavor into that. So it's going to be a great experience. There's also Zurich Rust Fest in Zurich happening as well in the summer, as well as, of course, Eurorust. And there is Rust Lab as well. So there's a lot happening this year. There's going to be lots more opportunities to interact, to get together, and to have a really positive experience. So please check them all out. I think some of the organizers are even in the room, so during the social, please look out for them, interact with them, and we hope to see you all at these different conferences. So please give them all a massive hand. Right, I want to say a big thank you. Big thank you to all our volunteers. Could you all come up? Lore, Senyo, Max, Tim. Am I missing anyone? Neil, where's Neil? Ethan as well, and Luke. All of our amazing, come up. Come on. So, these are the incredible people that made all of this happen. So please give them a massive hand. Thank you. Thank you. And please, during the social, connect with them, find out what they're into, find out what they're doing in Rust, and yeah, let's continue to grow and build together. I want to also ask the Vitis team to come up as well, please. Matt, Blue, Sam, Megan. Come on, give him a hand, Come on, all the Vitis team. Where's Sam? Where's Sam hiding? Where's Blue? Okay, so this is the amazing team that made all of this happen. There are other members who are hiding. They're not trying to come up, but everything nice that you've said to me, that you've said about me, it's all down to these amazing people who have taken care of the event space, all of the logistics, all of the nuts and bolts, all of the really hard stuff. So I couldn't have done this without them. Partnering with them has been one of the most, one of the best things. Yeah, mostly good. But these are the people that I lean on for everything. They have made this entire process smooth, and we've had a great time because of them. So please give them a massive hand. Right, so after I've slept for about a week, I'm looking forward to seeing you all in 2025. We're going to have a great time. And we have done so much to kind of build momentum. And I want that momentum to continue. I want us to all continue interacting in a positive way. Let's find more opportunities to meet in person. I think loads of really good things came out today. I saw so many clusters of people talking together and interacting and asking questions. So I just want all of that to continue. So again, thank you all for coming. And we're now going to head down to the social to have more fun. So give yourselves another big hand and see you all in 2025. Thank you all for coming.